Okay, then it's my pleasure to welcome everyone to this last and final meeting of the FarmConners Consortium. Sorry that we had to invite on relatively short notice, but let's hope that we can get some sort of a roundup of this particular project, which will end in a few days' time. But as you know, this kind of project never really ends, it just transforms into further activities. So, yeah, as usual, mute your microphone. We are recording. Tuhfe already mentioned that. We start with a little welcome and outline of the day from me, then go into two of the work packages before lunch, have another topical work package after lunch, and then go into the more administrative and outreach work packages afterwards. And we might also be able to conclude this meeting a bit early, which I'm sure none of you will object to. So the project is now in the last month. We had 2 contract amendments, the last of which only actually got through a few days ago, but we managed to get that concluded before the end of the meeting, before the end of the project, which is good. So there's some final reporting coming up, but we'll take that in the work package 6 section. And the first contract amendment had some extra tasks, but we already discussed those earlier. So we had this kind of a final Gantt chart, and what you can see is that here at the very end of the project, we really don't have that many deliverables. I think we pushed out one or two of the deliverables to the very end, and we'll be hearing more about that in the near future. So the narrative at the beginning was that wind farm control had been a research focus for a long time, and we've been trying to discuss how to actually get that a bit more into the market and how to pave the way for wind farm control, and how to also have some particular wordings a bit more defined that we didn't really have in the beginning. So we had most of the people we knew that had been doing wind farm control in the past. We also had some advisory committee that we, in the end, really didn't use too much, except we invited them to the meetings that, as you know, weren't really that easily possible anymore after the start, which is obviously a shame for something that is a project that is determined or is made to actually convene people and to talk to people. We had this layout of tasks and work packages, and the promise was that we came from a relatively low TRL to wind farm control at TRL 7. Whether that actually was true or not can be discussed later on in the final discussion. But some of the highlights definitely were that kickoff workshop in Amsterdam, where we had over 50 people together in a room. You remember those days? That was just before that little nasty virus hit our overall travel plans and ways of collaborating together. We also managed to get a workshop in Leuven after that, and both of those workshops are on the YouTube channel. One of my personal highlights was taking in that poster award on behalf of all of you at the Wind Europe Offshore Conference at the end of 2019. But we're still working on a few more highlights, and one of them is to do a paper on the grand challenges of wind farm control. That's nearly done, and we'll hear more about that in work package 1. There's also the benchmark results where we have a preprint available, and that's also a final deliverable for work package 1. Again, those are all teaser slides and shall be discussed in much more detail later on. We also had certification and standardization already in Outlook, which I think is a bit of the way towards the higher TRLs to be known that we already have some products and some ways to certify those products. And there's also the market showcases that obviously are some of the particular activities that we did in FarmConners. One of the things coming up is also this open access controller and the wind farm, looking into how to do the flow control and the power plant control together. And as an outlook, as I said, FarmConners is not the end of the line, it's not the end of everything. Wind farm control is a big topic and will only grow in importance in the future. And one of the things that is coming up now is the Awaken project in the US. It's notionally the largest ever project on measuring flow in wind farms and in large wind farms. And they also have a wind farm control component. If you haven't been there, check it out at their wiki location. It's hundreds of turbines, and they have just concluded the discussions with the landowners. So they will be starting putting up some of the longer term instruments already from May. And I think the main intensive measurement campaign is coming then next year. And of course, we also have a parent, which is the IEA Wind Task 44 on farm flow control. That doesn't really take the power plant aspects that much into consideration, but it's all from persons already involved in the FarmConners project. And if you haven't signed up yet, please make yourself known to either Paul Fleming or Jan Willem, who are the operating agents, and they will be happy to put you into that loop. They get a lot of different tasks, subtasks, where you relatively quickly see the connection to the FarmConners project. And finally, we'll have a review meeting on 26th of April, but that's strictly speaking only necessary with the coordinator, and the work package leads are invited to present their work packages. So this year is a bit of a dry run for this. But by that time, we'll also have to have delivered our final report. And as I said, we'll tell a bit more about that later. And that already concludes my first very quick overview. I'm trying to be a bit quick so that we can get a bit more time for the actual interesting discussions on the topical issues. So if you don't have any questions so far, I would invite Filippo or Carlo to take over work package 1.
Hi, I'm Gregor. I will share my screen. Do you all see it?
Yes, Filippo, thank you.
Okay, super. Yeah, I would like to just give a short update on the overall outcomes of the work package, and then we will look at the results for the benchmark. So just to summarize, these are the objects of work package 1. So the overall object was to increase confidence in the models and in the control strategies, And we identified 3 objectives. So aggregate the experience of past ongoing activities concerning the testing and validation of WinFarm control strategies, design a benchmark, and perform further validation of the available model and strategy through the benchmark so as to increase the confidence in the technology. We defined several tasks. The first one was like state of the art, so establish the present state of the art in WinFarm control testing and validation. And we had 2 deliverables. One was a workshop, and the other was an analysis of the research gap that was published in a paper presented at TORC 2020. Then the second task was designing a common benchmark. So first we had to reach a consensus among us, among the consortium, and then this was also another deliverable, and then another deliverable was the recommendation and best practices for testing and validating WinFarm control strategies. We then launched the common test benchmark. So this was done on a webinar. It was supposed to also be presented at TORC live, but due to the pandemic, since TORC was postponed and then was all online, in the end we decided to anticipate the launch of FarmConners benchmark through a webinar. And then also the benchmark that's been described in the overall goal of the benchmark has been described in the paper published at TORC 2020. Finally, the last task was the benchmark. So what we wanted to do was we validate model against the database, FarmConners database that consists of high fidelity simulation, wind tunnel experiments, and field tests. We wanted to use database to quantify and reduce the model uncertainties. And we expected also to see a convergence toward those strategies, those wind farm control methods whose benefit can be relied upon based on model predictions. And finally, we wanted to present the results in a journal paper to be submitted with Energy Science. Indeed, we had 3 benchmarks within our common benchmark based on synthetic data set, so large eddy simulations generated within 2 projects, 2 European projects, Total Control and CL Wincon. Then we had again a wind tunnel data set, benchmark based on wind tunnel data set from experiments conducted during the CL Wincon project. And finally, field data set. So a data set coming from field experiments. In this case, we were using data gathered while within the framework of the Smart Airway project. It's a project funded by the French government. So for each benchmark, for each of these 3 benchmarks, we consider 2 cases. So single wake and multiple wake. So single wake, basically we use SCADA data provided by a cluster composed by 2 wind turbines, and multiple wake is like SCADA data provided by a cluster composed by several wind turbines. In total, 13 participants submitted the results. So as you can see, 5 participants worked on the field data set, 4 participants on the LES-based data set generated in CL Wincon, and 5 participants on the LES-based data set generated in Total Control, and finally 2 participants for the wind tunnel data set. So the some results were presented first at the Wind Energy Science Conference of 2021, again online in this case, and this also is deliverable 1.6. And finally, we had deliverable 1.7, which is about the publication of the results, all the results from all the 3 benchmarks I just talked about, in a paper, in a journal paper. So indeed, we submitted a paper at the Journal of Energy Science. The submission was on the January 13th of this year, and is now the review process started. So it's we expect that will be reviewed in the forthcoming future, and hopefully finally published in a matter of few months. And finally, in last summer, some tasks were added to the project, also to work package 1. as the entire project was extended, and the task that was added is task 1.4. It is about prospects and challenges of wind farm flow control. And for about this task, the goal was to write the review paper that Gregor just spoke about. And it's a paper composed of 55 pages, 6 sections, more than 300 references. It's currently out for friendly reviews, but it is expected that will be submitted again to With Energy Science in a matter of a few days. Okay, so this is just an overview of the objectives and results and deliverables pertaining work package 1. And now I would like to invite Tuhfe and Thomas to also provide more information about the benchmark results. Specifically, Tuhfe will talk about the benchmark results based on LES data, and Thomas benchmark result based on the field data, while at the end I will also present benchmark results based on wind tunnel data. So I don't know who, Tuhfe and Thomas, who wants to start first. Feel free.
I don't know, field tests are always more interesting. Thomas, would you like to give it a go first?
I can go first.
Yeah, thank you.
Yeah, I need to share my screen. Okay, you should be seeing my screen right now. Okay. So I'm going to present you the field test results of the benchmark exercise. So even though I'm showing these results, most of the graphs you've been seeing have been calculated by Tuhfe in the scope of the benchmark exercise. Maybe I will start with a reminder of what this blind exercise consists of. So in the scope of the benchmark exercise, I provided some wind farm field data that comes from our own wind farm, which is a Sol du Moulin-Vieux. And it consists of 7 turbines wind farms in the northeastern part of France. And they are Senvion MM82 wind turbines. So we are in a very simple terrain. And in the scope of a French national project, we realized some wind farm control field tests on these 2 turbines here. Let me activate. Yeah, on these 2 turbines here, SMV6 and SMV5. And the upstream turbine was SMV6 because in this region of France, the wind comes from the southwest, yeah, and goes first to SMV6 and down to SMV5. We did both wake steering and axial induction control during these field tests, but the wake steering were much more conclusive than the axial induction control. So in the end, we only kept the wake steering tests for the benchmark exercise. So a bit more about these wake steering tests. So they comes from the second field campaign of the Smart Hill field tests. And during this campaign, the upstream turbine SMV6 was constantly misaligned by 13 to 15 degrees during a duration of about 6 weeks. And we could clearly see a wake deflection at the SMV5 turbines and also a bit downstream. So we could design 2 exercises using this data. One based on the single wake case, in which SMV6 is combined with SMV5 to constitute the 2 turbine cluster, and the multiple wake case when we increase the sector so that we also consider SMV4 to SMV1 turbines. And this is more like a partial multiple wake effects than full multiple wake effects. For the participants, we gave 12 months of normal operation data that they could use for the model calibration unfortunately, the data set was not large enough, and we couldn't provide wake steering data that could be used for calibrating their model. So they only have normal operation data for the model calibration. We could also provide WinCube data 6 months that were covering the full wake steering period, and also part of the baseline period, so that the participant could also use the WinCube data to help for the model calibration. So that's in the end what they use. I'm going to talk only on the single wake case here, because the multiple wake case were more or less giving the same outcomes than the single wake case, but the figures were not that easy to describe. So as Filippo mentioned, we had 5 participating models for this benchmark exercise. They were all engineering models. 4 of them provided time series simulation based on their model, and the last one, P17, were only providing static simulation, so binned values for this for the wake simulation. So maybe the interesting thing to comment on these participants, so P4 and P5 were using the exact same model combination, but they adopt completely different tuning strategies for their models, and this resulted in very different tuning parameters for the all models, and this is what you can see in the table here. So they were using the FAIRis model, and here you have the values for the 2 participants, and you can see that they are really different in the results. And in particular, the thing that have a very great importance, as we're going to see that later on, is the value n, which corresponds to the yaw loss cosine exponent that we traditionally use for decreasing the upstream power as with respect to the yaw misalignments, and this very different between the 2 participants. P6 also was the participant, I think, who put the more effort into calibrating the wake model, because he used a lot the WinCube data to characterize the atmospheric flow condition on the site, and also to tune better this yaw loss function as respect to the yaw misalignments. And I think that's the participant who spent more time in the calibration. And yeah, finally, the other models were not from participant consortium, but they use similar Gaussian model as the other participants. So maybe the first results we can discuss is the time series comparison of the for the 4 participants that provided this kind of outputs. And what you can see here is the difference between the observed active power at the wind turbine versus the predicted active power at the turbine. So the first one is the upstream turbine, and the bottom graphs are the downstream turbine. And you can see, for example, comparing P4 and P5, we are using the same model. They more or less have the same shape in the differences between the predicted and observed power. The difference is that P4 sees a much lower power using their model compared to P5, and this is mostly because the cosine exponent was much larger for P4 than for P5. And on the contrary, P6 shows a much better comparison with respect to the observed power, and this is mostly because thanks to their calibration, they were able to model a yaw loss exponent that was dependent on the wind speed, and therefore we see a much better relationship with the observed power. And P6 is also the one that behaves the best at the downstream turbine, but P5 is also doing quite a good job. Now, talking about evaluation of the different models. So we had these two sectors defined for multiple and single wake. I'm going only to discuss the single wake cases. And the pre-processing of the SCADA data was a bit difficult, mostly because since this is field test results, we do not have a reference signal because the atmospheric condition is changing constantly. So we had to use the SMV7 power as the reference signal, since this is the only turbine which is not affected by the wake steering. Although this turbine is very close from a forest, and therefore the wind that arrives to SMV7 is not exactly that the wind that SMV6 experiences for the full wake condition that was considered for this exercise. So we had to apply some recalibration on the SMV7 power signal so that it can be used as a proxy for SMV6 during the wake steering exercise. The second problem with this field test is that we didn't have any toggling between the wake steering and the baseline period. It was so we had to use a baseline period that was both before and after the wake steering period, and therefore there might be slightly different atmospheric condition in average between the controlled and the baseline period. So we try to make sure that these differences were not too difficult, we're not preventing the analysis of the results, and we think that the way we applied the post-processing was the one that was the best for for analyzing the results. So we estimate the results using the energy ratio methodology that was defined by the NREL. So basically, you use the reference power signal to normalize both the upstream and the downstream power signal as a function of wind speed and wind direction. And that's what you can see here for the single wake case, either as a line plot or box plots for several bins. So in red is the baseline operation. So the baseline wake combine SMV6 and SMV5 power as a function of wind direction. In black is the same, but during the wake steering test. So you can see that since the black box here is above the red box, we do have an increase in the combined power production of the turbine during this field test. And the other plots are the provided results for the wake steering tests of the participants. So what we can see is that in general, most of the participants are able to capture the wake steering effect. We can see here that all, for example, the full wake case at 205 degrees, most of the participants have their box plots which are very close from the black one. Unfortunately, it's not that clear for the partial wake case here, but P5 and P6 seems to be very well performing and able to have an estimation which are very close from the outcome from the field tests. And finally, we could also estimate the energy gains. So the energy gains are obtained by dividing all those results with respect to the same baseline here in red. and they are also expressed in terms of box plots. And the conclusions are more or less the same as the previous graphs. So in general, P5 and P6 are the ones who are the most able to capture the energy gains observed on the SCADA data. And P4 show big losses in power production above 210 degrees. And this is probably because their hypothesis on the yaw loss exponent of the downstream turbine is a bit too high. So there are too much power lost on the upstream turbine, and the downstream gain in their model does not compensate for this loss. On the other hand, for participants who estimated a much lower loss at the upstream turbine, there seem to be much closer to the actual results for the wake steering case. So finally, some conclusions from this benchmark exercise, maybe 3 major points we highlight in the paper. So first, there is a very high sensitivity to the choice of the model parameters. This can be seen by comparing P4 and P5, who are using exactly the same model, but with a different tuning strategy. We can observe very different results in the wake prediction. And in particular, the yaw loss cosine exponent seems to play a very critical role in this estimation of energy gains. So this might be the parameter that needs to be calibrated the more accurately. I precise the fact that there was no wake steering data to calibrate the models for the participants, and I think this is a very was a very problematic for the participants, because they had to take hypotheses about both the yaw loss cosine exponent, but also the wake deflection model. And some of the participants did a great job in calibrating those models without wake steering data, but for others it was more difficult to get some results. So using these first 2 points, we also could conclude that maybe for future field implementation, it would be easier to follow an iterative process, because at the beginning we are forced to use normal operation data to define a first wind farm control strategy, but we have no insurance that this wind farm control strategy will be the best one. And after a few months of wake steering implementation, we could probably update the wake model parameters based on the field data we had collected, and then adapt and adjust the wind farm control strategy to get to the, let's say, final and the most efficient strategy we can get. So that was the end for this this wind farm field data. I don't know if you have any questions and comments about this exercise.
Yeah, so feel free to unmute yourself if you have any questions. You can also post it on the chat before we go on to the other blind tests.
Hi, I had a question maybe. I was wondering, I guess in the beginning you mentioned that you did do axle induction control as well, but you decided not to include that. Could you maybe just say a few notes on that? What was the conclusion and any finding that you might have found from that study?
The axial induction field test, you mean?
Yes.
Yeah, the major problem is that we couldn't put the optimal axial induction control we wanted to, we had optimized numerically. We were forced to use noise curtailment mode of the turbine, which was not optimal. That theoretically it could have increased the power production, but when we implemented that on the turbine and analyzed the data, we didn't see any gain on the downstream turbine, and we were observing a loss on the upstream turbine because of the curtailment. So yeah, in the end, with this axial induction control field test, we didn't manage to increase the production of the turbines. Although we measure some gain in the loads, reduction of the loads on the turbine, but the production was lost. So that's why, yeah, we didn't have much data, so it was very difficult to design a benchmark exercise on this case.
All right, thank you.
Thank you. Any other questions? If not, Filippo, would you like me to continue, or you want to continue with the
Sure.
wind tunnel?
You
All
can
right.
go on.
All right.
Yeah, and present last.
Okay. Okay. Do you see the screen now?
Yes.
All right, with the LES blind tests. Okay, great. Yes, so I'll talk a little bit about the blind tests number 3 and 4, as we put it. Sorry for the voice. As we named it, so we started with the field test Tomo just showed, and then we also had the wind tunnel as the other blind test, and we had 2 different LES test cases, as Filippo mentioned in the beginning, to do the investigation. So the LES data set is typically used in the literature quite a bit. And it is also, when it comes to TRL, technology readiness levels, it is also seen as an enabler, if not the prerequisite to have the field implementations. So the LES itself is still giving us a lot of options to be able to dig deeper in terms of what type of behaviors we see in the wake. And we can also, of course, compared to field implementations, play with the control settings a little bit more, and also do maybe extended analysis, especially for the tools that are coupled with hydroelastic tools. However, here we are looking only at the power performances for both CA-WinCon and total control LES cases. They're produced with different larger dissimulation toolboxes, different CFD solvers, and they also have different sort of attributes. And I think they had both very valuable contribution to the overall benchmark, but they're also looking at different sort of parts of the wind farm flow control. So let's start with the CA-WinCon test cases. If I can change the slide, let's see. Here we go. Right, so it is based on the SOFA simulations, and then it is probably the most extensive database in terms of the control settings we have implemented for 2 different wind farm layouts. So maybe it's not so easy to see, but the one on the left is actually showing here. It is actually showing 3 turbines. And here we have 3 turbine rows times 3 of them. So in total, 9 turbine cases. So we're looking at 3 turbine and 9 turbine cases. Also, the spacing between the turbines are a little bit different. So we have 5D for 3 turbine cases and 7D for 9 turbine cases. The CA-WinCon original database is much more extensive than what we use in FarmConners. So we only use a subset of it in terms of the inflow at least. And then we're looking at this, what is referred to in the original database as A4. The whole database is publicly available because it's also deliverable from another EU project. So feel free to reach out to CENER contacts. All of it can be found in the FarmConners benchmark wiki under Contact Us. So please, if you're interested in using the database for other projects, feel free to reach out to us. Anyway, so for this particular case, we're looking at 7.7 meter per second, quite interesting field for the quite interesting range of operation for flow control, relatively low turbulence intensity. And for the calibration data set, as I said, we had a little bit more data available within CA-WinCon anyway. We have actually given 1 point of operation for the wake steering to be used in calibration, and that was around 20-degree upstream misalignments. Because it is 3 turbines, and sometimes we're looking at the multiple wake this time, there is actually secondary control as well. So it's not just the most upstream turbine that is controlled, but we always try to provide 20 degrees control settings from each of the turbines whenever applicable. The biggest downside though for the CENER simulations is that the simulation time is about 10 minutes. That means especially for the steady state participants, steady state models that have participated, it's a little bit challenging. So we should see all the conclusions with a grain of salt. So more of a proof of concept and analysis of the trends, but not necessarily the final validation. This is a numerical setup anyway, so it shouldn't be read as final validation, more like reference LESs. So for the CENER itself, here are the list of participants we have had. So 4 participants in total. We have both the steady state models and also quasi-dynamic runs, and you can see different fidelities. We had runs and we also had engineering models looking at the CENER LES cases, the blind test. So within all these models, the plots are a little bit different than what you've seen with Thomas. So let me go through them a little bit. So first of all, on the left-hand side, or on the x-axis in general, you will see all the turbine configurations that we're looking at. Because we're also looking at multiple turbine cases with several rows, it becomes very complicated towards the end. So please, first of all, try to have a look at the x-axis. Here we're looking at 2 turbine case. On the left-hand side, we have the first turbine steered or misaligned at 30 degrees counterclockwise, as you see. And then we have 10 degrees clockwise case, -10, 30, -30. So this is sort of number 1 taxonomy or the language jargon. And then on the y-axis, we will be looking at 2 different variables. So on the left, we have delta power, that's in absolute value. So you see in megawatts. So controlled operation minus normal operation at the first turbine and at the second turbine, at the downstream turbine. That's what we have on the left. And on the right, we have the box plots, which is a little bit more familiar, of the power gain calculated very similarly, like the results from the field tests. And then in this power gain, you will see where the medians are and also the range of the power gain expected. So we have the distribution plotted only for the reference LES, and we have put only the median values of the participating models here to have a little bit clearer view of the box plots. So what do we see overall is that we have, if the deflection is lower, so over there for ±10 degree cases, for example, the power agreement overall, the model agreement overall is actually a little bit better. But if we have, if we go for -30 degrees, for example, this is where we see the biggest model mismatch. And you can see also for most of the models, they are symmetric in the way that they provide results. So +30 versus -30 degree of misalignment is giving pretty much similar results, as you can see in most of the model performances. However, it's definitely not what is observed in the LES results. And here, if we actually dig deeper into what has happened in the -30 case, right here, where we have the biggest mismatch, we can look at the figure on the left. So that shows us what happened when the first turbine is -30 or 30 degree misaligned counterclockwise. The models are actually doing kind of okay job in predicting the power at the first turbine. So the power loss factor is not necessarily as off as we discussed for the field tests, but the problem is actually happening in representing or capturing the behavior, the losses at the downstream turbine. So there seems to be an overestimation of the wake. That means underrepresentation of the wake deflection that has happened for at least those 3 models over there for the large deflections of the wakes. Again, I want to remind you that the 20 degree were in the calibration data set, but apparently even 20 degree on its own was not necessarily enough to extend the results or extend the calibration, generalize the calibration for 30 degree cases. So that's another note we learned from this benchmark. That was for the single wake at 5D spacing. So this is the result of what happens if we increase the spacing a little bit further. So this is looking at 7 diameters downstream now. So that means we're actually looking at 9 turbine layout. For there, we had a little bit less set points. Again, -20 degree for upstream misalignment is plotted here. As I mentioned, it was in the calibration data set. So the good performance match over there is reflected with the model performance. But something interesting is also happening. So we seem to have a bit of higher likelihood of the power gain for the 10 degree upstream misalignment versus 20. 20 is actually risking power loss quite a bit. And then we have again, higher likelihood of power gain at 30 degree upstream misalignment. That is also an interesting behavior on the LES part. So if you look at the model mismatch again, for the biggest mismatch that we have in the largest deflection angles, then it is a similar behavior we've seen with the 5D cases, meaning that the wakes are overestimated at the downstream turbine behind the steered wake, and the deflection of the wake is underrepresented. This is actually observed in some of the models, underperforming models over there, in other LES cases as well. So it's not the first time those participants, let's say, were not necessarily too surprised when they saw that the higher deflection angles were actually mismatching and they were overestimating the wake losses. All right, here we're looking at the multiple wake results. Again, still with the total control cases. This time we have a lot of cases, so I hope it's not too overwhelming. I suggest again to have a look at the x-axis first in terms of what box plots represent. So here we have 3 turbine configuration. The first 2 are perfectly aligned, and the third one is 0.5 diameters laterally spaced, as you can see over there for the third turbine. We have different control combinations, control settings or wake steering settings combinations for the first upstream and the first downstream turbine. So you can also see how they're changing. So the first one over here, y minus 10, would mean first turbine is 10 degrees misaligned, and this second y minus 10 is second turbine is also 10 degrees misaligned, and it's changing that way. So if you look at the box plots first, so the first 2 refer to 0 upstream misalignment, a little bit of downstream, first downstream misalignment. This one is 10 degree upstream misalignment, and these other last 3 are 30 degree upstream misalignment. Since the trends are very similar, depending on how much the most upstream turbine is misaligned, we can say that the most upstream steering is the main driver for the power gain behavior, at least looking at this LES. This has also been shown in one other study, which we have cited in the paper before, so feel free to look at that for details as well. So it's not the first time it was observed, but it's sort of complementary on that regard. And then we have the most significant model mismatch and large power gains for the third turbine that was laterally displaced a little bit. If you look at the differences, here we're looking at minus 30 case. So the first 2 turbines are minus 30 degree misaligned. We are just zooming in into that box plot over there to see the model mismatch. So if you look at the very last turbine over there, you can actually see the power difference. So controlled operation minus normal operation at the very last turbine in this 3 turbine configuration, it goes all the way to plus minus 1 megawatt. That gives us about the uncertainties that we've seen, or in general, the variance that we can expect even with LES for already more than single wake situations. So let's look at a little bit more uniform rows. This time for 9 turbines, we have 3 rows, 3 parallel rows, as you see. The control settings are applied per row. So the first row and the second row of turbines, and then the most downstream turbines, if you will. So here in this first box plot, all the first turbines, all the upstreams are misaligned for 10 degrees. And then the downstream turbines are misaligned for 10, 20, 30 degrees. So the distribution of the downstream misalignment is changing. Here is the same for the second turbines, but the first turbines are minus 30 degree misaligned. And here there is no misalignment at the downstream turbines at all. So the results are quite interesting because this time, first of all, the power gain levels are quite high. So if you see for the especially for the minus 30 degree upstream steering, the likelihood is more than 10% for the power gain in 9 turbine configuration. So that is quite promising. But if you look at the model results, it's hardly captured. So you can see again, the insensitivity of the results, if you will, if we go further down for the misalignment degrees. But also if we have a zoom in the biggest model mismatch, so that's the figure in the middle over there. Here we're zooming in. You can see for turbine 1, 4, 7, the models are matching very well. These are the upstream turbines over there, the most upstream turbines. But for the other 2, the models start to produce more and more results, more and more errors. So again, these errors are actually accumulating further down. So the predictions at the second row are a little bit better than predictions at the last row. And then when you start having all these 3 parallel rows and add the errors, this accumulates a lot at the wind farm level. So the overall model mismatch or model inaccuracies are quite high, higher than a single wake anyways. Right, so that was all for the CIAM-INCON cases. Now we're going to be looking at total control AES cases, which has a lot simpler control settings. So here we are controlling only at turbine 32 and turbine 29 here. So the two upstream turbines right there. And they're actually, one of them is misaligned with 20 degrees counterclockwise, and the other one is 30-degree counterclockwise. We'll be looking at the differences. What is interesting, one of the interesting features in the total control case is that the average wind speed we're looking at is a little bit more than 10 meters per second, so 10.4, which is kind of close to rated wind speed. So we are in this interesting power curve region, very close to rated. So it's nice to be able to investigate the controller's performance. The sensitivity is also quite high over there for the controller implementation, which we will discuss in a second. So because it was a relatively limited data set, the calibration was based only on the normal operation. So we could not provide even a single setting like we could for CIAM-INCON for total control cases. So it is a little bit like the field implementation, almost completely blind test case here. However, we had a longer simulation time. So this is all the way up to 1 hour. That means we can actually look at the whole time dynamics and see if it's correlated or not. Total control is also interesting because of the participants profile. So what we have over there is a medium fidelity model, so Högste Farm that's coming up. And we also have Strat Farm, which is somewhere between low to medium fidelity. And then we have a RANS model over there. And then we have a low fidelity here, and then we have another LES here to compare. So this is pretty much the highest fidelity distribution of our participants for the blind test. So looking at the results, especially in the dynamics and the correlations, are quite interesting. So here we have the first result. We're looking at a single wake. This time you will realize on the left-hand side, we have the actual time series for the first time. So not sort of binned or averaged per turbine sort of settings. And on the right-hand side, we're still having the box plots. So right-hand side is a little bit more familiar. And again, on the x-axis, we have two different control settings, 20 and 30-degree upstream misalignment. The turbines are always 5D apart in total control, as I said, and we're looking at the single wake here. So the black ones are the reference LESs, and the participants are color-coded as usual. So if you look at the, first of all, if you look at the variances, it's quite striking. Here, first of all, we're not looking at the power gain, we're looking at the wake loss reduction. That means how much the wake loss was under controlled operation minus how much the wake loss was under normal operation, divided by the normal operation. So we can see that, especially in terms of wake losses, the variance is quite high. So you can see for the reference LES, the median is about 20%, for example, for 20-degree upstream misalignment. But then the variance goes all the way to 60 to minus 20%. So that's quite high. However, the overall trends or the recovery, the wake recovery potential is increasing with increasing upstream misalignment. That's nice to see also. So for the medium and high fidelity models, meaning the green and the pink being the other LES, and then this being the Högste Farm, so medium fidelity tool, we have a good agreement, especially for P8, and the dynamics seems to be captured well. So this is also nice to see, and it's also visible at the time series on the left. You can see the fluctuations are quite correlated as well for the medium and high fidelity tools. All right. If we look at the power gain, so from wake losses to power gain, the picture changes a little bit. So here where we see the controller implementation and the turbine representation playing an important role, especially or also fueled by the region being close to rated. So we're already on the high sensitive region. So although, for example, the participant 8 was having very good agreement capturing the dynamics when it comes to wake losses or wake loss reduction, it is underestimating the power gain quite significantly. And that is simply because of, first of all, again, the turbine representation under control conditions. So the yaw losses at the control turbine is becoming harder to capture. No calibration data set was available. And also the wake profile might be different. So all these details are discussed in the paper, so go ahead and have a look. However, when we look at the comparison of the two LESs, so pink and black, it is actually quite refreshing. So for the so also, let's look at the variances because this is interesting. For the second LES, we seem to have a faster controller response. So the variance is actually a lot broader. You see also in the box plots, and is further emphasized for higher steering, as you can see. And then, as I said, the good agreement between the black and the pink, so between the two LESs, is actually quite good news for the TRL levels of the control technology. That means we can expect correlated behavior between the LES models. So it gives us a little bit more confidence, saying that they can be actually proof of concept or they can be used for numerical validation. So here this time we're looking at multiple wakes. So of course the overall power gain effects or overall mismatch is also decreasing a little bit when we start looking at such a big row with only upstream effect, upstream misalignment effects. But the trends are still continuing. So two LESs agreeing very well. However, the fluctuations are also getting quite high. So it's getting harder and harder to say something concrete when we're looking at several wakes when it comes to power gain via wind farm flow control. All right. So for all the analysis and further description of the participants and everything, feel free to have a look at our preprint under discussion currently in Wind Energy Science, but you can read the whole PDF already. And it would be great also if you can leave comments over there. Certainly we will take them into consideration in the revision phase. Right, thanks a lot. Let me know if you have any questions.
Thank you, Tuhfe. There is indeed a comment in the chat.
Can you read? Let me see if I can see it.
Yes, given by Soren. It's about the overestimation of the wake can also be due to not properly capturing the variation of the thrust coefficient when the turbine is yawed. Indeed.
Oh yeah.
A combination of these effects. Yeah,
no, definitely. It certainly can be the effect. It's just the misrepresentation or underrepresentation of deflection was already proven for the models we were looking at. But I think it's a fair point also that the CT behavior is also changing for the steer turbine. And maybe there's underestimation of CT, just like the power loss factor, right? It needs a calibration as well. Yeah, very good point. We can perhaps add that in the discussion bit also, in the revision of the paper, sorry.
Yeah. Yeah. Okay. Other questions or comments from the audience?
All right, then I stop sharing.
Yes, I will then share my screen again. Please go back here. Okay, so the last benchmark, I would also like to have maybe last point. The last benchmark made use of experimental data coming from wind tunnel. These data were gathered during the CL WindCon project. And the wind tunnel is one of the polytechnical wind tunnels. So we did tests in the upper section here. So you see the wind tunnel of Polytechnical is closed circuit wind tunnel with two test section. The upper one, in the upper one, it's possible to reproduce, to simulate boundary layers, atmospheric boundary layers. And there is where the tests were performed. It's quite large wind tunnel with a test section of 14 of width and 4 meters of height. And we used three, in terms of wind turbine model, we used up to three wind turbine, scale wind turbine models named G1s that have a diameter of 1.1 meter and are fully automated, equipped with individual pitch control, torque control, yaw control, as well as many sensors on board the turbine to measure loads, as well as many other quantities like rotational speed, power, pitch angle, yaw angles. This is the view of the cluster of 3 turbines that was used during the test. So you see the 3 turbines were spaced 5 diameters. The turbines were placed on top of a turntable that can be rotated so as to simulate different incoming wind direction. And also it's not visible, but upstream of the cluster, we had the pitot tube that in the end was like the mast of our cluster, so was providing the measured wind speed. So in terms of inflows, we performed tests with we simulated two different boundary layers. One that is typical of offshore environments, so like a turbulence of 6%, and the other of onshore environments, so 13%. We mapped the flow on a vertical plane upstream the cluster for both inflows. And here you see like a distribution of the speed, longitudinal speed, normalized with respect to the speed measured by the pitot, located here. And you see that the flow is clearly non-uniform. It's not uniform not only along the vertical direction, because we have a vertical shear, as is shown here, but also a little bit along the lateral direction. This is just due to the presence of, we can show it back again, presence of obstacles at the inlet that are not uniformly distributed, or rather the fact that the turbines the wind tunnel is equipped with 14 fans. There are supporting structure here at the inlet, supporting a net or even a heat exchanger. All these elements make the inflow being not uniform, also in the lateral direction. These mappings were provided also to the participants. We had two participants only. However, one participant used 4 different models. Indeed, we have participant 3 that used either a Gaussian or super Gaussian wake model with uniform or spatially varying inflow. So with uniform inflow, assuming that if the inflow was on average uniform on the entire section, while spatially varying inflow means that the inflow was considered non-uniform also in the vertical and lateral direction. As you can see here, so the participant 3 for different models. While participant 18 only one model, and participant 18 based the model on the Kian Ishihara wake model. And here is like a detailed of the models that were used. In all cases, anyway, the wake was assumed to have a Gaussian shape. What is also important to stress, despite calibration data set was provided, it was not used, and indeed all participants decided to use the default parameters. So the parameters that are available in the literature and the references where the models are described. So as we said before, we had 2 test cases, one single wake, the other multiple wake. When it comes to single wake, we gave to the participants data that were measured while testing a single G1, single turbine operating at 6 different year misalignment angles, from -40 to 40, for both inflows. The data that were given to participants were simply the wind speed measured by the pitot tube placed upstream of the turbine, and the G1 control input, so nacelle orientation, collective blade pitch, and rotor speed. What was required to the participants to provide average wind speed and turbulence intensity at several locations at hub height and at 3 different distances downstream of the rotor. Indeed, what we did was we measured the wake shed by the G1s for different inflows at different distances from the turbine and for different misalignments, and then we compared measurements against prediction. This is just a figure that shows all the measurements we had and also the prediction that were given us by the participants. What I want to say just about this picture that we also best fitted every measured or predicted profile of the wake at height with a Gaussian curve, and it is shown here. I mean, maybe it's not that easy to see, but here in the stars, the black stars are the measured data, and you see there is like a black line passing through the measured data, and that is the best fitting Gaussian curve. So what we did with these best fitted Gaussian curves, we were able to estimate wake width, wake deficit, wake center position, and these allow us to compare such features. So wake deficit, wake position, wake width, what was measured of the measured wake and the predicted wake. And here you see a picture showing all the quantities. We can focus first on the wake deficit. So generally, as you can see, it's quite well captured, especially by the super Gaussian models. So you have these two lines here, green and brown. The green line with the square, and also the brown line, orange line, sorry, also with this cross. And generally, there is a well captured trend, especially for high turbulence intensity, no matter also the yaw misalignment, but the trend is very well captured. For a moderate TI inflow conditions, so like 6% turbulence, the wake recovery appears to be slightly higher than what has been modeled. So if you see here, the wake deficit is reducing as we look at different distances downstream. The observed wake deficit is reducing quicker in a faster way than what has been predicted by the models. And this is clearly indicate that the wake recovery rate could have been tuned according to the provided calibration data set. If we still look at the wake center position, overall we see a generally very well captured trend, especially by the super Gaussian models. Indeed, I mean, it's the observed measurements, the observed wake center position that are in the black lines quite overlap very well with, again, the green line with square mark, or the orange line with cross marks that are really overlapping quite well. When it comes instead to the wake width, what we saw that all models tend to slightly overestimate the wake width, and so the mismatch is quite significant for yaw conditions, as can be seen here. So in all these cases, whenever we are looking at high yaw misalignment, minus or plus, for example, 40 degrees, we see that the wake width that was the measured wake is much smaller than the wake width of the predicted wake profiles. We trace back this reason to the fact that all models assumed Gaussian-like shape of the wake, and so they are not capable of capturing the shape of the typical shape of the wake when a turbine is yawed. Such shape is the shape of the shape is more close to kidney shape, so called the curved shape, and this could be one of the reasons, especially at up height, while the predicted wake was characterized by a bigger width than what was observed. Then we looked at multiple wake case with these are the list of tests that were conducted. So concerning multiple wake case, we did test with two aligned G1s. So two G1s perfectly aligned one after the other. Again, the spacing of 5 diameter. And we look at two different operating conditions. First case, where both turbines are operated misaligned of an angle of 30 degrees. And second case, where just the upstream turbine is operated misaligned of 30 degrees, and the second one is kept aligned to the wind direction. And the other case was two turbines that was laterally spaced of 0.5 diameter. And again, two cases here, one where downstream turbine is yawed, the other one on the upstream turbine is yawed. Finally, also we had data coming from experiment conducted with 3 turbines aligned or 0.6 diameter laterally spaced. And again, here in this case, we tested 25 different combinations of yaw misalignment for the 2 upstream turbines, while the third one was always kept aligned. So again, what we gave to the participants were inflow data, G1's control inputs, and what we asked when testing with 2 turbines, we asked to provide the average wind speed and turbulence intensity after the second G1, so at the distance of 7.5 and 10 diameter from the very upstream turbine, and with 3 wind turbines, just the produced power. So here you see like the comparison between the measured wake and the predicted wake. So here you see that the wake has been measured at 2 different distances, 7.5 and 10D. This is for the case where both turbines were misaligned. This is for the case where just the upstream turbine was operated misaligned. We asked the participants to provide the wake profile along a horizontal line located at three different altitudes from the ground. So at first at hub height, and then at a distance at a location lower than the up height, so 0.36 diameter lower than the up height, and then 0.36 diameter above up height. So if just looking at this case, when both turbines operated misaligned, what we can see generally that there is quite a good trend between measured and predicted wake, especially when the super Gaussian model is used and when the non-uniformity of the inflow is considered. So you see that the trend indeed, the match between measured and predicted quantity is quite satisfactory. On the other side, when only the upstream turbine was zeroed and the downstream one was not, we see some quite relatively poor match, no matter the models that can be used, especially if we see here again at up height, but also at other locations. Generally speaking, the match is not as satisfactory as was observed, for example, when looking at the wake shed by a single turbine, or as was observed, for example, in the previous case, when both turbines were operated misaligned. And we try to, we thought that one of the reasons could be that the models didn't account for the effects of secondary steering that indeed can produce quite some effect in this case, as despite the second turbine is not operated at misaligned condition, still the yaw misaligned condition of the upstream turbine could have an effect anyhow on the wake shed by the second turbine. So leading to a displacement on the lateral direction of the wake shed after the second turbine. Similar conclusions were observed in the other case when we were looking at second turbine lateral displace of half diameter. So here you see again, in this case, just the downstream turbine was zeroed. In this case, only the first turbine was zeroed. Again, when only the downstream turbine was zeroed and the upstream one was not, there is quite a good match, as can be seen. Again, especially when considering the super Gaussian wake model and when accounting for the inflow non-uniformities. Again, instead, when only the upstream turbine was zeroed, the downstream turbine was not, you see that there is quite strong mismatch between predictions and measurements. And again, this can be explained by the lack of modeling of the secondary steering effects. Then we looked at the comparison between power. So you see on the x-axis, the measured power, on the y-axis, the predicted power for the first turbine, second turbine, third turbine, and the entire cluster. So these data, these graphs report data that were measured when the turbines were operated aligned, so with the wind direction 0, let's say, and also when the turbines were laterally spaced of 0.6 diameter, so wind direction of approximately -7 degrees. And here again, we have data that were recorded with moderate turbulence intensity on the high turbulence intensity. So if you look at the first turbine, we see generally here, also there is in the plot here, it's also reported the normalized root square error. So as can be seen that when using inflow mapping, so when accounting for the inflow non-uniformity, we can get a better agreement between measured and predicted power for the upstream turbine. When it comes to the second turbine, we saw that with the best predictions were again observed with the super Gaussian, when the super Gaussian model was used, as can be observed here by this error. When it comes instead and the comparison on how it's quite satisfactory. When it comes instead to the third turbine, what we say that in many cases the produced power is underestimated. So models will tend to underestimate the power produced by the third turbine. And specifically, we saw that the biggest differences the biggest mismatch was observed for moderate turbulence intensity and for full wake conditions. So this indicates that whenever there is a strong wake to turbine interaction, whenever there is the wake is characterized by a strong deficit and the downstream turbines are fully immersed in the wake shed by the upstream, there is where we notice the major mismatch between measurements and we observe the major mismatch between measurements and prediction. And again, as you can see, there is not a clear trend which model performed better. However, overall, when looking at the cluster, the discrepancies were lower than what observed at turbine level, and this is quite interesting. So despite there was a difference at turbine level, however, when looking at the cluster, the power of the cluster, the differences between measurements and predictions reduced quite substantially, and indeed we had like a normalized mean square error of just 2%. And what we saw that the super Gauss model provides the best accurate prediction, also when accounting for inflow non-uniformities. Then similarly to what has been done before, we look at gains. So given the data that we had, we first looked at which was the combination of ion misalignment of the two upstream turbines that provided the maximum power gain with respect to the baseline, to the normal operation. And this information for the optimal ion misalignment for the upstream and downstream turbine is reported in this graph. And then we look at the power gain. So when the turbines were operating, were misaligned of the optimal value, how much more power was produced by the entire cluster with respect to the case of normal operation. So turbines all aligned with respect to the wind direction. So if we look at the power gains, we see that clearly, as expected, we have the highest gains in partial wake condition. So when the turbines are laterally displaced up to 0 kilometers, and lower gains are observed instead observed for when turbines are fully aligned, so fully in the wake. The downstream turbines are fully in the wake shed by the upstream turbines. So if you see comparison between prediction and measurement, generally there is quite a good match, especially again when looking at the super Gaussian models, no matter with inflow mapping or not. Generally, there is a quite good match. There's just some deviation here in this case. So the models overpredicted the gain that can be achieved by steering the turbines if the turbines are all aligned and the turbine's intensity is quite moderate. However, there is quite a good match. Concerning the ion misalignment, the optimal ion misalignment, this is also quite interesting. Because the optimal ion misalignment, so the ion misalignment of the upstream turbine that maximized the power output, was very well predicted by the super Gaussian models for the upstream turbine. You don't see, but the lines are exactly overlapping, they're all on top of each other. For the downstream turbine instead, it's a different story. So all models tend to, on average, overpredict the optimal ion misalignment for the second turbine. Indeed, as can be observed, based on measured quantity, the optimal ion misalignment for the downstream turbine for the second turbine should be lower than the optimal ion misalignment for the upstream turbine. However, such trend was not really captured properly by the models. And again, this can be due to secondary steering effects that were not, the models did not account for. So for concluding, we say that we had quite reasonable predictions, despite none of the models were ad hoc calibrated. There was margin for calibration, as has been showed. So we can expect that if the models were calibrated using the calibration data set that was given, prediction could have even be better. What we saw that the wake modeling can be improved. So we can think about, definitely we should think about modeling the wake so as to capture its characteristic curve shape. As we saw before, just when looking at the wake shed by a single turbine, the wake width in misaligned conditions was not properly modeled, was not properly estimated, predicted by the models. And also we can think about accounting for the effects caused by secondary steering. When we look at the power production cluster 11 gains, power gains, they're generally accurately predicted. There are significant discrepancies for turbine 3. This is similar somehow for first and second turbine. We had good results, similar to also has been what has been shown by Thomas for the field data set. But when looking at the third turbine, we do see some discrepancies. This is also similar to what Tuhfe has been showing before concerning about the LES-based benchmarks. So this could be again, the main reason could be lack of secondary steering effects, inappropriate modeling of wake superposition. However, at cluster level, there is a good agreement. So like the mismatches tend to compensate each other, which is good. And the gains are also predicted with sufficient accuracy. Yeah, and this is also the end of this benchmark as well. The presentation of results for the last benchmark. So I wonder if there are questions and comments from the audience.
Nothing on the chat, Filippo?
Nothing, yeah. No. So it seems that there are no questions. So I think overall, just to conclude, I think the trend is we were quite satisfied about the outcome of the benchmark, especially the comparison between measured field data, wind tunnel data, and model predictions were quite satisfactory. So this is definitely quite a good sign. I would say that yeah, there are still differences, especially when we start looking at after the second turbine. So the third turbine, there are some mismatches observed, and probably we need to focus also in that sense to try to improve the modeling so as to capture better the available power of the third turbine, and as well as also came out from the field data set, it's important to also from the LES data set, it is important to account probably of the power losses due to yaw misalignment. This is also another major impact. Yeah, there is a message.
Yep. Irene asks, do you think the further benchmarking would be necessary after current conclusion?
Yeah, I think there are areas of improvements, definitely. So we saw that there are areas of improvements, especially I would say when we start looking at after the second turbine, because that's quite clear message. If you look at second turbine, looking at field data set, wind tunnel data set, LES also up to a certain extent, but the match seems quite satisfactory. But if you look after, so I think our models should be improved in this sense. There is a lot ongoing in this direction. Try to improve better wake superposition models, better capturing effects like secondary steering or others. So it could benefit in the future additional benchmarks, mainly focus on these other aspects. So I would not focus anymore second turbine. I will look deeper in the array to see if we can capture there as well also the power and the effect of wake steering on power. But definitely I would think doesn't mean that we need to generate new data. Maybe we can also think about using what we have. But definitely could make sense in the coming future.
Large wind farms, right? Also,
Yeah.
maybe another thing that we didn't look here is the other objectives, right? So we've always been looking at power gains and maybe on the wind speeds to support the discussion on the power gains, but we did not have enough participating models to say something meaningful about the loads, right? So that would be also interesting to look at. And we will see a little bit more in work package 3, maybe additional objectives in terms of revenue can also be added. That could be another benchmark on its own. Yeah, certainly. It's the first of its kind though, but it's it's a basis. It doesn't cover it all. Yeah.
Yes, and I think these activities, similar activities, will be performed, I think, in the forthcoming future in other projects or IA tasks. I'm quite confident.
Yeah, there are already discussions going on that I would expect so also. Yeah. All right, shall we conclude work package 1 then?
Yes, I think we're already late, so sorry. We should go on.
It's all right. We have quite a buffer for this in the calendar, so no worries. Thank you so much, Filippo. And yeah, thanks a lot for the work package one, which was validation exercises. And then we are moving with work package 2, and that will be presented by Andreas for the certification and standardization discussions. Oh, you're muted, Andreas.
Yeah, right. Thank you, Tuhfe. And thank you, Filippo. So this was a good bridge from the prediction of the wake situations to the loads might occur through all those different control issues. And I track now screen 1, screen 2. All right. So this is not what I wanted to show you. That's what I wanted to show you later. Sorry. Right to the beginning. Here we are. Sorry. So can you see my slides?
We have it. Thank you.
Okay. Yeah, we, as you know, looking as a certification body from the certification and standardization side, not just on the benefits or on the gains, on the power performance improvements, but on the safety levels and the structural integrity. So meaning we are not the ones that maybe want to stop or limit wind farm control. We want to make it safe and sure and economically acceptable. And we have 2 basic certification and standard sets accepted worldwide. This is the IEC scheme for certification of wind turbines, OD 501 and OD 502. And right now there is no clear description in this international wind turbine standard on certification of wind farm control. It is just mentioned in a side note. And there is the DNV standard for certification of wind turbines. We have several standards for onshore wind turbines, offshore certification, project certification, and floating wind certification. And herein there was an update in 2020 where wind farm control has been mentioned in the project certification. So basically the offshore wind farm certification, where a site-specific design assessment should be updated if you include post-installation wind farm control into your software, into your farm management, or if you would plan wind farm control right from the beginning before the installation in the planning. And the basic approach mentioned there was because of the many uncertainties in the effects of wind farm control to start or to require a measurement campaign on the individual wind farm to confirm that the loads do not exceed the ones that have been assumed for the standard operation in the wind turbines. This is basically a requirement to what you have done in the benchmark test, but for each and every wind farm. It is, of course, a high effort for each operator. So we looking forward to develop more reliable certification approaches to overcome the requirement of measurements within the certification path. But right now, as we know, we have this uncertainties in the prediction of effects. We have somehow to mitigate those uncertainties. Yeah, here's again the list of standards that are relevant for wind farm control, mentioned in our position paper, deliverable 2.1. And I jump now to the current deliverable, which is in the very finalization phase. And I'm really happy to complete this now. We have given a look to the grid operations requirements, because beside certification typically covers the wind farm up to the grid connection point. But on the grid connection point, there is another certification type active. This is the grid code compliance, which is often separated, but somehow we have maybe here a link in certification of those two certification schemes. This is expressed in section 2. In section 3, we have analyzed the load effects on turbine level, and I will show you right now then the results we have made together with TU Munich, Filippo and Helena Canet. And we have explained the new methodologies of LongSim, the simulation tool. I will not go into details in this today. And we have made recommendations how to certify those effects, wind farm control strategies in the future. Yeah, in the sensitivity study we have done, we have looked specifically into the wake steering strategy. Thomas Dück explained the testing and the results in their wind farm, and we can see the positive effects on some load reductions, and we can see the positive effects in power increase for the second row turbines and the rows behind. But we have also to keep in mind that we have to consider the probability of the coincidence of extreme events with this extreme yaw misalignment situation. So wake steering operation plus a extreme event has to be considered, because we think about 20 years of operation lifetime, and we assume that at least once in those 20 years operation, the turbines will see an extreme event, and probably in the near future those probabilities will increase even more. So the probability is realistic that wake steering plus an extreme event occurs somehow during the lifetime of a wind turbine. And therefore we have those load cases we simulate, and which have been validated in the past for the individual turbines on and offshore. And those are the load case group 1 during power production, 1.1, 1.3, 1.4, and 1.5 have been considered in this sensitivity study with TU Munich together. So we look at normal operation, we look at extreme turbulence, we look at extreme wind direction changes. And by the way, we had a nice storm last weekend here in northern Germany, I think in Denmark too. In my neighborhood, a number of large trees were fallen, and we had strong direction changes and gusts during this storm. And those are the simulations, those are the situations that are simulated in those load cases: extreme wind shear, extreme direction change, extreme turbulence. And this has been combined with yaw misalignments up to 38 degrees, because typically yaw misalignments or wake steering strategies range from 20 to 30 degrees. And if you have, and we considered a yaw error, a measurement error of ±8 degrees, which is also in the standards. So we come up to 38 degrees yaw misalignment. Here you see the 4 load cases considered, and each of those load cases had about 3,000 load case variations. So quite a number of turbulence simulations. And we have done those simulations with 3 turbines, all reference public domain available turbines. You have to say that those turbines all have very simple control algorithms and maybe are not 100% comparable to the state-of-the-art large wind turbines with very sophisticated controllers. However, this study had the intention to show qualitatively how extreme events plus yaw misalignment behaves and how this relates to normal operation, just wind aligned with the rotor axis. Yeah, we have made those simulations with 2 different codes to have a scatter here also in the simulation tool. As I said, the idea was just to give a qualitative impression how wake steering, how yaw misalignment could affect the load picture. And here you see how the deviations of the models have been in terms of flexibility and eigenfrequencies. They have matched quite well, I can say. One comment to the models is, of course, that they both used a very similar BEM simulation, blade element method approach, which has restrictions, limitations at the simulations of those high yaw angles. However, we have said that the qualitative result is sufficient here, and we can apply those BEM method in this yaw consideration. This is a very interesting summary result that T-Unique made from this study. We have 6 different locations at the individual wind turbine. The blade root pitch moment, the blade root flap and edge moment, the bending moments, the tower top for aft moment, and sidewise moments. So the loads at the connection point from the nacelle to the tower, and last but least, the tower bottom moment. This is representative for the DTU 10 megawatt reference model. And in the number of bars you see in the middle of each bar package, we have the normal operation in between plus and minus 8 degrees. And at the borders of each column, you see the extreme yaw misalignments and the effect of the different load cases. And when you look at the borders of the columns, for example, for the pitch moment, figure A, you see clearly that we have for high yaw angles and load case TLC 1.3, for example, the extreme turbulence intensity, we have high load increases. So the pitch system gets loaded if there is a coincidental combination of extreme turbulence and yaw misalignment. We see this, for example, also in this tower top side moment, or figure E, that plus and minus yaw misalignment angles have significant higher loads than the normal operation without this yaw angle. So the overall conclusion is here we have clear and clear indication from both tools, from 3 turbine variants, that extreme loads, ultimate limit state loads could increase. And here we have shown this over the range of wind speeds. When does this load increase happens? So on those figures you see in black line the normal operation with wake with yaw misalignments -2 to +8 degrees, and you see in the red line the overall wake steering summary, and we in the red line we have the average, the maxima, and we have also showed the box plots to show you the variation of the load cases. What you can see here for the blade root, for example, blade flap moment and blade edgewise moment, that there is a clear increase of the loads, of the ULS loads above rated wind speed, basically. But there are some in the range of rated wind speed it starts, but it's definitely in all simulations above rated wind speed we have increases of blade root loads. Same situation can be seen for the tip to tower clearance, so for the blade bending, which is basically related to the figures we have seen before. So the tip to tower clearance for high wind speeds and high yaw angles becomes a critical situation. And for the tower bottom bending moment, we have we can see here not this obvious picture, but also in certain wind speeds load increases. This analysis led us to the question, or to the consideration, what would we do if we limit the wake steering approach and limit it, for example, just in the operation between partial power mode, so between cut in and rated wind speed. And if we would cut out yaw misalignment above rated wind speed, how this then looks like in the load. Another idea was if we limit the wake steering mode just to certain degrees of angles, so maybe only up to 20 degrees yaw misalignment, which then gives you a lower effect in wake steering, but you might prevent higher loads. And here you see the relative coefficients. So this coefficients represent the load levels of the representative strategy compared to the normal operation with just plus minus 8 degrees, your error. What you can see is that without any limitations, so if we would drive wake steering up to plus minus 83 degrees, 38 degrees, we would have load increase in the range of 20% for even up to 40% in some cases, but this is just simulation, but definitely an increase. So when we look to a limit just on the wind speed, this is figure B, just 12 meters per second, then we have an average of 10% increase, and in one case up to 30% increase for the fore-aft power bottom moment. Looking at figure C, we have the same situation, much more reduced loads due to this restriction of the yaw angle up to 20 degrees. And then if we would combine both limits, even that, and say we apply wake steering just up to rated wind speed and just to an angle up to 20 degrees yaw misalignment, we come into a reasonable operation or load increase range, which might be covered by the existing design envelope of a wind turbine. So no increase any above 20%. Basically, it's in the range of 5 to 10%, what we see here is those limits. So this might be an idea how wind farm flow control could be applied, that there are setup limits and which have been then confirmed by simulations and by maybe also by measurements, that the design limits are not exceeded. All those experience we have made here in FarmConners and also with the benchmark results, we would like to include in our new standard. This is recently under update. This is the load standard ST0437, and we would like to bring in a section on wind farm control and on flow control and how to handle this in the future. So, as I mentioned right in the beginning, that we have already an included approach to have a semi-empirical approach already present, that we can certify wind farm control if it's accompanied with a measurement campaign. We would like to update the site-specific design assessment with a description of the wind farm control system. We would like to offer the possibility of certification on risk-based approach, so with failure mode identification analysis, for example, FMECA. This is engineering common practice that if you have not large experience and standards operating with including experience of decades of technology operation, then you perform risk assessments according a certain process, and you derive safety factors and safety levels with this risk-based approach. And this can be applied to wind farm certification as well. And we have derived in DNV recommendations for load case amendments, and I would like to introduce them also to you. Right. Yeah. Coming to certification, it is a common practice that when you want to certify a system, you submit a design basis, which gives you a complete description of your system and the way how you have designed it and how you want to assure a safe operation. Such a design basis typically lists then also the standards and the hierarchy of the standards, which standard you have applied then in the certification. So what we would like to suggest in our new standard is that this design basis should include the specification of the wind farm functionalities, the definition of the assets and the components, so the hardware of wind farm control. How the principles are and the control loops, the specification of the operation times. That's of course very important for the load simulation or for the consideration. How many hours during the lifetime do you expect is a certain wind farm strategy, down rating, axial induction, wake steering, how often this will be active, how many hours? The communication system is of course a sensitive point where how wind farm control system is communicating with the wind turbine, with the wind time controller. So what are the interfaces? Are there maybe different programming language active? Is there something like a wrapper necessary? So those things should be described in the design basis. The possible malfunctions. This goes into the direction of the risk-based approach. If you want to install a wind farm control strategy, you have to thoroughly look what failure modes could occur during the installation, during operation with wind farm control. And there should be a kind of analysis included in the design basis for the certification of wind farm control. Cybersecurity is relevant for all software packages in operation. So there should be something mentioned how this is assured. So, and proof wind farm features. Yeah. We have the operation limits given by the OEM of the wind turbine, and it must be, and those limits should be listed again, and it should be shown that those limits are all kept, even though we operate in wake steering mode, wind farm, power reduction axial induction, etc. So this is a first draft of a checklist, what to be hand in for the certification of a wind farm control system. Then we would like to make recommendations for the performance of the site-specific design assessment. So the check of the situation at a specific site with a specific wind direction, wind distribution. And we would like to introduce an updated independent load analysis considering the wind farm control effects as we have done it in the sensitivity study. So looking at those yaw angles, looking at those operation modes combined with the extreme events, looking also on the fatigue side, on the hours of operation in certain modes and how this impacts the fatigue. Also with the load reduction effects you could expect, for example, by the wake steering for the row behind. Those should be analyzed. And in certification of wind turbines, it's state of the art that there is one testing campaign for one wind turbine type necessary. So we would like to ask that those testing requirements adjust for the wind farm control operations, that wake steering operation is then part of the type testing of the wind turbine. Yes, this is a final table where we have listed all load cases and made comments on how to handle those load cases in a certification of wind farm control. And looking just at the very first four, those are the extreme load cases I presented in our sensitivity study. It's exactly that we would like to see a demonstration by the wind farm operator that he calculates the normal operation and compare it with situations in combination with wind farm flow control here. So with wake steering or axial induction. One comment here is, for example, axial induction often goes aligned with power reduction and load reduction. However, it might be the case that axial induction bring the operation mode into another rotational operation regime. So we have different excitations, different rotation modes, which might be in line with eigenfrequency of some components for some tower modes, blade modes, and then we have higher vibrations. So axial induction also is not necessarily brings load reduction, but it could bring higher fatigue loads. So for example, for the load case group 2, in load case group 2, 2.1, 2.2, 2.3, turbine failures are considered in combination with certain wind conditions. and the probability of those failures is, of course, difficult to combine with wind farm control. So here we, for example, think about that a risk-based approach for the failure mode load cases would be the right way to certify and to calculate load cases. Jumping then to the load cases under extreme, probably those load cases are not relevant for wind farm control anyhow, but just if there would be some strategy that impact the turbine operation in extreme wind speeds, so load case group 6 and 7 under 50-year conditions, and the turbine is in idling parked mode, then this should be considered, but I don't expect that this is relevant. So overall, we think that we have made a good progress here in getting first a perspective on the effects of ULS and FLS loads due to wind farm control. We have looked at the safety systems of the individual wind turbine, and and I think that with the next standard we would have a better way of certifying wind farm control rather than the recent approach with accompanied measurements and extension and of the certificate up to the completion of this measurement campaign. So, looking forward to your questions.
Thanks a lot, Andreas. Indeed, we have a few in the chat. I'll maybe give the word in order of appearance. So Gregor, maybe you want to voice your question first?
I think you answered some of that already. If there's, and I'm taking Mahmoud's question here as well, if you only do that for certain wind speeds or certain turbulence intensities and restrict it for there, then that might be a way forward. And I think you answered that yes, exactly, that's the way, that's the thinking that you're having currently.
Yeah, exactly. So you should then, of course, demonstrate that at those limited wind speeds, the load effects are below the type certification limits. And there is already a commercial product by Siemens, Wake Adapt, which is exactly already working with those limits. So
okay.
This is so.
Thanks.
Already in practice.
Okay, great. Irene, you want to voice your question first, and then maybe the comment as well.
Yeah, well, my question is also probably answered after the final slide. Was about the consideration not only of the stream events that may be critical, but also regarding the fatigue, normal production fatigue load cases like DLC 1.2. And you already said that this has to deal with the occurrence, the frequency of occurrence to weight in the fatigue calculation. Probably, yes, taking into account the wider yaw misalignment ranges, right?
Yeah, exactly. So this has to be done on each and every wind farm site, of course, individually. This is something you can't certify on generic conditions because the wind direction distribution is so different on each and every site that you need a consideration how many hours I have in operation during that wind direction and that wind direction. And
okay, thanks.
And this will be complicated indeed for
Yeah.
to capture those data. It's not easy to capture those data and to bring them into the simulation then.
Sure. And the last comment was, yeah, that in task 44 in work package 3 that we are colleaguing with TU Delft, we are working on defining the hardware and infrastructure needs, make an analysis of the different control technologies for wind farm control. And as you mentioned, some aspects that may be required to the certification, it will be great to have those aspects included in the analysis. And I see in the chat that your colleague Kai may help on that, so that's great.
Yeah.
Thank you.
Good. Thank you, Kai.
All right, thanks everybody. So like again with the queue. So
Filippo has a comment.
That's right. We have questions, but on the queue a little bit beforehand though. But Filippo, do you want to add something on the already ongoing discussion? Then go ahead.
Yeah, I had a thought because including fatigue definitely could be challenging, especially at the light of what Thomas concluded after his presentation, say that when it comes to wake steering, it could be convenient first apply it and then use the data to tune the numerical model, and then with the tuned numerical model conceive a better wake steering strategy. So it's definitely challenging if this is the path to take, because you can't foresee in advance that easily how much a turbine will have to be steered depending on where it is located. So it's definitely a challenging aspect.
Yeah. So I think condition monitoring would be then also maybe an approach that you install a monitoring system which is recording then the real situation and flag an alarm if you overspend the hours of certain modes of than expected. And then you have to look how you reduce the operation maybe, or then there are coming other certification approaches into force. But it's difficult. I would like to say that one approach for the fatigue could be in the simulation that you do with so far long sim. So such simulation tools pre-analyzes to identify the most loaded turbine and simulate the fatigue then on a subset of turbines with then bladed or other wind turbine codes, so that you not calculate this for all turbines, but you select based on a flow control simulation, farm simulation, the highest loaded turbines on certain parameters, tower bottom blade route, some indicators, and then calculate them in detail with those flow conditions, turbulence intensities, directions, hours of wind farm control operation in existing simulation tool like Bladed or CP Lambda.
Well, speaking of the tools, maybe Paul Brand's question will tie in here also better. Paul Brand, do you want to voice your question?
Yes. Hi.
Hi.
So thanks for that. So the independent load assessment today is part 2 for turbines.
You a little bit louder,
Sorry, the independent load assessment today is in Hawk 2 for turbines. Do you envision a park independent load assessment tool like a farm or something similar, where you have flow and air elasticity modeled, or is it just new load cases for Hawk 2?
you have to do a pre-analysis with a tool to estimate the flow conditions for the unfavorable position in a wind farm, and then you calculate those positions with Hawk 2 or bladed, applying those flow conditions you have found in the wind farm control farm simulation.
Do you have any quick follow-up question? Do you have any, say, pool of tools that you see fit for that first assessment of the flow that you then later apply?
They are not commercially fit right now, as I see. So we have to work with those beta versions available right now. But I think we have to start with those tools, and I'm pretty sure that they will develop fast and will be validated by the next commercial applications.
Thanks a lot, because there is already, as you said, there's a commercial product, so I expect already certification is ongoing or have happened. So there's a need for something until these tools are there. Some guidance on that. Yes.
Yeah. Okay. Yeah, well, as a side note, by the way, we're working on the validation for Hawk 2 farm, so it can also maybe be used. Exactly. Just a side note. Yeah. All right. So David has a question regarding the loads on the foundations. David, do you want to voice your question?
Yeah, thanks, Tuhfe. Yeah, I'm no loads expert, neither on turbines or foundations, but what I've heard from colleagues is that we're doing a lot of work on the turbine loads for the certification. I'm wondering how big is actually the impact of wind farm control adding to loads, especially those turbines that are on the lead rows, and if you have wind roses that have very predominant main wind directions, and these turbines might be operating under your offsets quite often. How do you see the impact on the foundation loads, and how does that need to be tackled in the certification? Is that a completely separate process? That needs to be done by the turbine manufacturer together with the foundation designer? I'm just wondering, and especially for offshore, of course, where you might have very different types of foundations, depending on your local conditions.
So the process works as follows. First, we have the rotor nacelle assembly, and this comes typically with a type certificate. So the rotor nacelle assembly has been certified for a generic set of wind turbulence conditions. And there we have those classes. We have class 1A, which is highest wind speed with highest turbulence intensities. And we have class 3B. 3 stands for low wind speeds and lower turbulence intensities. So we have those classes. Type certification covers the envelope for the machine. And then we have a wind farm with specific foundations, specific towers and specific foundations. And those site-specific towers and foundations will be approved in this site-specific design assessment I mentioned in the presentation. This is the part what we do in certification to check the conditions of the foundation and the tower. And we see those effects on the foundation. I have showed tower bottom results for the reference turbines under your misalignment. We have increased loads also for the foundation. And this is what I said, a site-specific design assessment has to check those conditions and has to recalculate the simulation, has to recalculate the loads with wind farm control application on the foundations. On the ULS side and on the FLS side, under consideration of the probability of the time used during the lifetime used for wind farm control operation. But there is definitely an effect, and the effect is checked in this site-specific design assessment. Okay.
Thank you very much, Andreas.
Thanks.
Any other questions? Okay, if not, shall we also conclude work package 2? All right, then it's time for lunch. We actually managed to keep the time within ±3 minutes, so pretty good. Then we'll see you back in 1:15 after the lunch break. See you, we'll continue with work package 3. Very interesting results there too. And then we'll go a little bit more on the administrative and outreach work packages. Thank you.
Thank you. See you.
See you in a bit.
Thank you. Enjoy the lunch.
You too. I'll resume the recording. Welcome back, everybody. We are continuing with work package 3. So Konstanze, thank you for sharing your screen already. Please take it away.
Okay, thank you, Tuhfe. Yes, so we will now present work package 3, the electricity market integration. And there were many people contributing, and those listed here are just those that will present on behalf of the others. So just as a quick reminder, you can't see it. What were the objectives of the work package 3? Because we call it, as I said, electricity market integration, and the idea was to further motivate the faster and more efficient commercialization of wind farm flow control, with a focus on the ancillary services and economic yield increase. So it has a bit of different angle than the other work packages. More specifically, the first objective was to investigate the state of the art of the ancillary services and the potential value creation there, to define a market showcase, to quantify the benefit that wind farm flow control could bring with variable electricity prices, and then also to take a look on the design phase. And from the dissemination point of view, yesterday I tried to just collect everything that we did. So we have 4 journal papers, 1 conference proceedings. We had a total of 4 conference presentations, 1 additional session organized by this work package, and we organized a workshop, a webinar, and we have a data set with the documentation on GitLab. So this is just what we will now, like just overview, and all this was part of 4 tasks, where the first 3 were the originally planned, and then we extended work package 3 with the 4th task. And yes, now we will take you through the tasks, so task by task, and tell you a bit more like this list, like what did we do there and what are the main points that we achieved. So then we start with task 1, the value creation. And for that, the deliverable was a workshop that we organized in Leuven. Gregor already mentioned it. And okay, here you see the agenda. So I just wanted to show you that we had a number of speakers from the FarmConners consortium itself, but also, for example, Ivan Pineda from Wind Europe. And the idea and how we collected the speakers and the presentations were that during this first workshop in Amsterdam, we realized that people are either working with wind farm flow control or wind power plant control, and that in FarmConners more people are focused on wind farm flow control, but should maybe know a little bit more about also the electrical aspects, and that's where the workshop focused on. Yes, so in addition to the presentations, we had some discussions. We discussed, for example, that there's an evolving value of wind farm flow control, what could be the key areas for value creation, and then also which tools would be needed. And all this we tried to reuse them in the other deliverables. Yes, and again, so we really met in person. I think for many people it was one of the last work travels before the pandemic. So I think just because of that, it became a more important deliverable than expected. So that was already task 1. And now we have task 2, the market showcase. And there we were so motivated that we wrote an additional journal paper that was no official deliverable that we usually refer to as Irene et al. And therefore I will also give the word to Irene to present you this work.
Okay, thanks. So can you put the next slide, please? Okay, so well, when we were preparing the FarmConners showcases, there were long discussions, and I remember it was already during the lockdown, very interesting discussions within a multidisciplinary team, and I have to thank all the participants for such a good exchange. And we found that we had more material and more interesting points than those that could be covered within the conference paper for the Wind Integration workshop. And we said, okay, we also found that there was a need, we detected a need for multidisciplinary approach, since we have under the wind farm control several disciplines involved, those more related to the power electronics electrical side and those more related to wind farm flow control. Well, I'm not going to use the to flow control, let's say. And also that we were having some problems with the vocabulary when we wanted to refer to a specific concept, and it was hard to find a common understanding for all the disciplines. So we try to make an approach, first splitting the different components, analyzing themselves, and then trying to give more prospect, and this is in the subsequent paper to that one, on how to integrate. So this was also the idea to give the basis for overall wind farm control objectives, and we also think that it was valuable in terms of references as a reference work to start with. If, for example, we are working in flow control and want to know more about the electrical side. Other objectives that we were covering with this paper is that it was a way to present in more detail FarmConners showcases without the length extent limitations, and also that it was a way to reach a wider audience than the conference, also looking for motivating participants to the showcases. So next, please. Yeah, and one of the first points we found quite difficult was on how to refer to the approaches that were already in the literature. That in some references we were finding wind farm control used either for the electrical side or for the flow side, and we came up with this suggestion. It's always open to discussion to the community, but one that we found quite useful, on using wind farm control to refer to the like an umbrella term to the integrated control for wind farm, where we already have quite mature wind power plant control from the electrical side, and the new wind farm flow control that it's in a less mature stage, let's say, that needs to be integrated in existing controls. Okay, so next, please. And a way of starting to make such a discussion and thinking, as Konstanze was saying, the work package objectives on how to provide services to the grid and how flow control can contribute to that. We made an overview of electricity markets and ancillary services so that we could use more rigorously the the vocabulary and the concepts that people from this field already use, and a way to properly refer when we are trying to create papers and so on. So there was an analysis, a brief analysis, and with good references to follow up afterwards on the different markets that we find mostly from the European point of view, and also some description of the ancillary services on how the time scales of the services are provided. Next, please. And then we came up with this figure that took a lot of discussions, and people involved know quite well. Where we wanted to put too much information, we became aware after publishing, and this was treated afterwards in the subsequent paper. We wanted to put how the controls may be interacting, on how to start studying this interaction, and also plotting there the services. So indeed, we have in the horizontal bars, we have the time scales of the services, which are not strictly control functions, but how long this service can be provided. And for those, for example, that are quite fast, then the flow control may not have nothing to do, say. For example, if we are talking about fall right through, FRIT, or fast frequency reserve. So in that part, it wouldn't make sense to focus on flow control. And we were also referring to the different controls that can be in a power plant, in a wind power plant, like well, globed as a converter and wind turbine control, those functions that are in the servo part, servo control at turbine level, and also the electrical control at the converter. Then the power plant control, which is currently in place, the green line, and then the dashed green line of the farm flow control, on how this could be somehow be integrated. And then probably misleading term, but the high level control, where we were thinking about either clustering of wind farms or having energy management systems in hybrid plants. Okay, so we made, based on this, some analysis of the interactions between the wind farm flow control and other control levels, and also made some recap, not as extensive as the Grand Challenges one, but some small compilation of the flow control technologies. Next, please. Next, we made an overview of the capabilities that the flow control could provide for grid and electricity markets participation, and raised some challenges that could be there if the flow control wanted to provide a higher added value. There was also a section, quite interesting section, on certification of wind farm flow control. This was prior to all the work in work package 2 for the final deliverable that Andreas was presenting before. So some analysis was made on how the communication is quite relevant, the communication of the farm flow control with the turbine safety system, which is at the utmost priority on how to maintain the integrity of the asset. Then load effects on turbine level due to farm flow control, which is more completed by the deliverable in work package 2, and some mention to how the certification of grid stabilization requirements is done so far and how it should be considered. Next, please. Then, with all this in mind, we try to make some prospects on how farm flow control could be further adopted thinking on that the wind power plant is not isolated in the production. It has to provide, and this is going to be increasingly in the future, it has to provide services to the grid, not just take maximization as the sole objective, maximization of power, and made some suggestions of key areas of value proposition for wind farm flow control in this context. So, for example, that we could make the optimization of flow control taking into account price-driven operation, which is the approach in the FarmConners showcases, the way to have greater flexibility in the operation, how to deal with assets life management in terms of structural loads, which is not taken into account in power plant control. Then how to make a better active power reference tracking when some reference comes from the TSO. Then the combination of power prediction and tracking with power maximization, which is a full combination of objectives there, and also to make a better available active power prediction, taking into account the inter-turbine interactions. And yeah, we try to map all this. So next, please. Yeah, and we end up with the description, more detailed description on the FarmConners market showcases that probably in other meetings you've been aware. I don't know, Konstanze, if you will explain afterwards on that, probably with the other paper. And yeah, and with all that, we raise some conclusions and some lines of future work. So many thanks. I don't know if there are questions. No questions? Okay.
Yeah. Otherwise, you also have maybe time afterwards. Okay, and then we continue with the FarmConners market showcase that Irene mentioned. And for that, we are finalizing the paper right now. So the paper will be submitted in the next days to Wind Energy Science. Again, as a repetition for you, what are the FarmConners market showcases? Basically, they are data sets of electricity price and wind inflow that should be used as an input to wind farm flow control for a reference wind farm. And as the reference wind farm, we chose the total control reference wind power plant with 32 turbines, but we find also a subset shown by the triangle for high computational needs. And we then the data sets were created in energy scenarios where this wind farm, the total control reference wind power plant, was hypothetically placed close to Hornsrev 1 in Denmark. And yes, so that's the energy scenario simulations are more explained in the paper that Irene just showed you, for example. But also on this, so when we decided, we asked for, it was open for everyone to participate, and we published it in Irene's paper. Then it was published presented also at the Wind Integration Workshop. We created a website with more information, and in addition, there was a special webinar for that. It was again presented at the Wind Energy Science Conference last year. And then we had announcements at LinkedIn and the FarmConners webpage. And if you're like wondering a bit more about the energy scenarios and the simulations, I recommend you to check one of those references. But after calling so many times, we had at the end 5 participants. And from those, one used the data set to simulate a single wind turbine. I will not further show that. I recommend you then to read the paper that we will soon submit. But this participant used different objectives, combining revenue maximization and damage equivalent load. And it's also really interesting, but I would now like focus more on the other 4 participants that used either the subset with 10 turbines or the whole total control reference wind power plant. And important here is that these FarmConners market showcases is no quantitative comparison between the participants and their models. So it's in contrast to the benchmark. But we rather wanted to analyze qualitatively and relate to the normal operation. In this case, comparing the results from one participant using wind farm flow control to those from the same participant with the same code, but without flow control. So just using the same input. And we defined, as Irene mentioned before, we had 3 showcase sets defined originally, but this final paper now will focus on the high prices showcase. And for that, we have 2 years. We have data for 2020 and 2030. And here you see the price rows. This showcase data is binned in the wind direction that you can see in the circle. And then we also have it binned according to the wind speed. And this is, we have 7, 9, and 11 meters per second starting from the center for each of the sectors. And the radial extension shows the number of samples per bin. So this was a fixed quantity depending on the showcase set. And then the colors finally show the prices for those different wind speed and wind direction bins. And as you can see here, there are some similarities related to the number of samples per bins, but the prices differ. For example, if you look at the Western wind inflow, we have here higher prices in the 2020 scenario than here in the 2030. In this case, I have to say relatively higher because the prices for 2030 are in total higher in these showcases. Yep. So first we looked at the normalized power gain, and here I show you now the results for 2 participants. One is the pink plot on the top, and the other one is on the bottom, the purple one. On the left side is for 2020 price series, and the other one is for the 2030 price series. That was the price series I showed here. And here, the normalized power gain means that the power gain using farm flow control is normalized by the normal operation for each participant for this particular bin where we have plotted. And yeah, as you can see, so okay, again, the radial extension was fixed due to the number of samples per bin. But what you can see here clearly is that there are differences. For example, for wind directions from the north here, for around 0 degrees for participant 3, we have a high power gain compared to other bins, while this is not shown for 2020 for the violet participant. That's just now to point you to some of the differences we observed. And when we compare the 2 different years, we can also see that, for example, for the plots on top, for eastern wind directions, there were some bins with a high power gain related to the others. Those are not that distinct for 2030. So here the colors are not as dark, but instead we have here a bit more higher colors for southern wind inflow. And then we compared now for the year 2020 in this case, the power gain and the income gain. In this case, I chose to show you the 2 other participants on top. That was the participant using the 10 turbine wind farm, and the other one, the whole total control reference wind power plant. And what we can observe here is is that it's different. So usually, I mean, it's often maximized for the power, but when we maximize for the income, for example, those bins here for 315 degrees on the outer circle get in relation way higher income compared to what you would have expected from the power gain. And also at the bottom, you can see there it was for the power gain, it was more or less evenly distributed over all bins. While when we look at the income gain, it's clearly that those outer bins here with wind from the northwestern directions produce a higher power gain. And then another thing we looked at was the income gain per turbine. Here you see for each participant 1 bar for each of the turbines, but I will just show you some examples. For example, for wind turbine 1, 2 of the participants had negative income gains, and this turbine was placed here at the outer edge of the wind farm. And similar, the smaller wind farm that had no turbine 1, but had here a negative income for wind turbine 13. And when we, in addition, take into account the wind power rose for, the price rose for the same year, we see that there are many bins with wind directions from the west. So they are often the turbines that are in the first row. So there the control strategies decided to change the operation of those turbines in a way that the other turbines will gain more income, so that in total there was a higher income gain. Yes, so that's what I decided to show you. Just to conclude on this, it seems like that maximizing power is not necessarily always the same as maximizing the income. And since this was the first study of its kind, we suggest that it should be further investigated how electricity prices should be considered or could be considered in the wind farm control and the operation. Another point I wanted to make is that we had no participants for the other 2 showcase sets that we defined, which were the low prices and those driven by the transmission system operator. For the low prices, we said that we would require a load neutral. So the same loads should be kept or they should be reduced. It might be the reason that there's no kind of good way to include structural loads in the control objectives. So this is a research gap, and also for the transmission system operator that defined we defined a power reference. I would also say that wind farm flow control and research didn't look so much into reference tracking. Okay, I'm not sure if there are questions about the showcases. Okay, then we will continue with the design phase. That's the new task, and Thomas will present it and share his screen.
Okay. You should be seeing my screen right now. So I'm going to give you a quick summary of activities on the task 3.3, which is the design phase. Basically, wind farm control has been mostly focused on improving the performance of operating wind farm. And the idea within FarmConners were to start to think about what would imply wind farm control from the beginning. So how, considering that we can use wind farm control in the operating phase, how will that influence the consumption of a wind farm? So to answer this question, we had planned during this project to organize a mini symposium at WESC 2021 to discuss about this issue. and then write a report that were supposed to summarize the presentation and the discussion during the session. So this was not planned as an official deliverable, but it was still published on the FarmConners website. So if you're interested in reading it, you will be able to download it from the website. So this design phase session was hosted at WESC 2021. Unfortunately, we couldn't have a on-site session due to the COVID pandemic, so we were forced to have it online. So that kind of reduces the interaction compared to what we had planned at the beginning. Thankfully, we had 4 speakers coming from 4 different institutions, and we had great talks about this design phase implementation related to wind farm control. So here is the table of the people who talk during this session, and the topics were really different from one another. So we had one topic on how you can use wind farm control to optimize better the layout of a wind farm from the beginning, from Christopher Bay. We had one talk related to the relationship between grid and flow control, and how you can better design the grid integration of a wind farm with respect to wind farm control. Then we had one talk on the bankability of wind farm control, so how you can prove when you want to finance your wind farm that wind farm control will provide extra energy for the AEP and the calculation of the P90 for financing a wind farm. And finally, one last talk from CENER about how wind farm control could be used to reduce the loading or improve, for example, the wind sector management of a wind farm thanks to a better modeling of the WEC. So in average, we have 55 to 60 people attending the session, with a peak at 68 people in the middle of the session. And the report gives a quick summary of each presentation, and also all presenter slides are attached to this report. So as a conclusion, during this task, we first had the opportunity to discuss the benefits of wind farm control in design phase. And this topic is seen to be very large. There are like very different thematics that can be discussed and related to this topic. We only discuss very shortly about 4 of them, but there are many more that could also be discussed. And I think that's more work and research will be expected in the future on this topic, and it will just gain importance in the upcoming years.
Thank you, Thomas. I think that's something to look forward to for everyone. I guess there are no questions, or do you want to surprise us?
I do have a comment, though, not really a question, but just to support Thomas' argument on we will see more in the future, but in the Grand Challenges paper, and that is a part of Work Package 1, we have a whole section dedicated for co-design process that also looks at, of course, design phase, but layout optimization, etc. So over there, one of the things also together with the market showcases, when we had the subset of the wind farm versus 32 turbine layout, so the higher the wake losses, the higher the gain overall, also in terms of income to be expected from wind farm flow control, right? But we also say wind farm flow control can actually help with densification of the wind farm, meaning increased loads, increased wake losses. So we can densify the wind farms potentially if we can demonstrate the effects of decreased loads. And then with this further increased wake effects, we can even have further benefits of wind farm flow control. So that's a very nice sort of feedback loop, if you will, that can actually be demonstrated further in the future. I'm looking forward to see the works also on that realm.
Yeah. Thanks for the addition. That also shows how well interconnected the FarmConners packages are.
Yeah.
Okay, the next part will be presented by Thanasis, who led the simulate model of the task 3.4, that is this additional task of the work package. And yes, we can see your slides.
Let me change the correct screen. I hope you can see my full screen now.
Yes, perfect.
Yeah, perfect. So yeah, we were given this task about development of a Simulink-based framework for the integration of wind farm control. And there were a few people involved from TU Delft and from TU Munich, and that was a very interesting interaction. So the overview of the task, you have been introduced to work package 3 and the targets. Deliverable 3.5 is what we're focusing on here. Is this integrated wind farm control and wind power plant controller framework. The requirement was that it should be in it should be open source first of all, and it should be in MATLAB Simulink due to industrial practices, I guess, and modularity. At least 2 reasons. The motivation, of course, behind that is, apart from the motivation of investigating wind farm flow control, that most of the flow control related studies usually disregard both realistic wind turbine control operation and interactions, but also wind power plant electrical control aspects, or active power, you could say, control aspects. On the other hand, most wind power plant control studies usually disregard farm flow. And of course, for realistic implementation, both of these interactions need to be integrated within the same framework. So this led to the main requirements of looking into such a framework. And here's the overview of the top level block diagram in Simulink. The focus again is on modularity, but also interaction. So we want to see the interactions between the different disciplines. But we also want to see to have a capability of replacing modules with different fidelities and so on. So what we have here in the release we have now, we have in the center a recursive block that calculates n number of turbines, where the turbine dynamics and their individual controllers are calculated. So this runs in a loop. Then we have the on the left the power plant control, which you could say that this is the wind farm control because it includes both the power plant control settings, all the set points, where in the dispatch of the signals, the flow control aspects can be integrated. I will go through, zoom into details as we move along. Then in order to test this model, of course, that's not the target of developing the model, but in order to test it, we had to integrate a flow model, and TU Munich work on that and integrated a version of FAIRis in a simplified way to be able to run the model with the flow. So zooming in on the wind turbine controller part, what we have here is a pretty simple representation of turbines. Of course, it's just a 1 degree of freedom drivetrain model that depends on the integral inertia. And then the CP, CT values are a function of distribution pitch angle, but also yaw angle, which are pre-calculated, right? We tested the model on the IA 15 megawatt reference wind turbine, representative large offshore turbine. And the turbine controller part is an as accurate as possible Simulink representation of the DTU wind energy turbine controller. That's an open source controller that's already in Git for many years now, highly validated with a lot of industrial features. And this includes derating modes. We have 3 derating modes available, but also, and on top of that, an industrial yaw controller with moving averages, windows, and functionality that you would typically see in an industrial application. So the inputs to that blocks cover the local wind speed and direction for each turbine, and the distributed power set points and yaw set points from the wind farm controller. And the output, of course, is the power, both available, calculated, there, estimated, and measured, the actual one, and then CT that goes to the flow model and the individual wind turbine direction. As you can see, the model is pretty complicated. Actually, you could say that the wind turbine control block is the most complex of the whole model. The flow part is based on integration of FAIRis with Python, with pretty typical wake models. TU Munich work on that. You could say it's a pseudo-dynamic implementation because it's not actually quasi-steady dynamic. So it's called every time step of the wind farm simulation, but there's a simplified wake advection calculation that makes sure that the changes are propagated with time accordingly to the downstream turbines. What else? On top of that, there's very simplified added turbulence fluctuations to kind of, in a simple way, include turbulence on top of the steady state signals. So the input to the module are the ambient inflow wind speed direction turbulence density, the CTs of the individual turbines and their orientation. And of course, the output we get out of that, the local effective wind speeds directions that are fed back to for calculation of the turbine dynamics, but also the projected distances between them with, calculated with the flow direction in order to account for the simple wake advection. On the wind power plant or wind farm controller block, we have a simple collection system where cable losses are calculated. So for the measured individual power signals, they're fed here, and then there's a power plant controller with all the typical operation modes. So MPPT for maximal power point tracking, balance modes for a specific setting of production, and delta modes as a function of available power. And then there's the dispatch, which just sends the global set point and yaw also signal to the individual turbines. And of course, you can imagine this is exactly where the wind farm flow control integration can take place. So the main outputs, of course, are the power set points and yaw set points individually for every turbine. We have a first test case of the model just to demonstrate some of the aspects we want to see there. It's a pretty simplified case, an array of 4 turbines at 5D. And then the first test case concerns the wind power plant control. So no wind farm flow control settings, just power plant control settings with and without the flow model. So what we have here is a realistic inflow, ambient inflow and direction, wind speed direction turbulence density provided by TU Munich. And indeed the specific duration of 2 hours that we demonstrate here, we made sure that the wind direction is around the full wake. So it is plus 5 degrees from a theoretical full wake direction. And then we have the 30-minute mode switching. So we start from a balance of 0.4 and we go to a delta mode of 0.2, and then we end up with just MPPT mode after that. So we run this in this complex inflow and see what's happening. Some of the main results we see on the left, the dispatch signal. So that's the global power plant dispatch signal that then is equally distributed on the turbines without considering wind farm flow control aspects. And then we see that we have this balance mode and then the delta mode and the MPPT mode. Of course, in the delta mode, since available powers, one includes wake losses and the other does not, we have different settings being provided to the turbines. And of course, we see the response in the estimate available power. This is purely an impact of the wind farm flow effects that are missing on the black one. And then on the actual measured power, we see that it is almost the same in the balance modes, and there's a clear delta varying, of course, with wind speeds between the case where we don't consider flow effects and the one where we do for delta and MPPT modes. But of course, it's interesting that since we have all the detailed dynamic simulation of every turbine, you can look at the individual response signals. So we have for each turbine the available power and the measured power. And you see there that the first turbine for every case kind of matches the no wake situation. But of course, the ones downstream will react differently with and without wakes as expected. And this influences, of course, the local CT provided by these turbines, but also the local operation settings. So we have the individual turbine directions here, and of course with a no wake flow. There's only one signal, the black line. You could not really easily see it here, which is equal for all the turbines with no farm flow, but there's a lot of individual different reactions to the direction when we consider wave farm flow as expected. And the same with the operation of each turbine, given rotor speed and pitch setting and generator torque. This is just an example, and you can identify a lot of interactions, of course, between the controllers and the modules here. But as a second test case, TU Munich ran a realistic inflow, the same data set again, different segment of that, to focus on wind farm flow control implementation using the same framework. So they offline optimized wind farm direction, so settings, turbine direction settings, so yaw misalignment settings using Floris as a function of wind speed, and then for each turbine, and then they implemented that only in MPPT modes. And this is a segment where we have from low wind speeds to above rated, and both full wake, partial wake, and no wake situations based on the direction of the ambient direction. And you see, of course, the expected small gain in the cases that you have high yaw interaction here on the turbines. I don't think I have the quantification of that yet, but that's of course not the focus of the study. But yeah, that's it. That's what we try to show with this modular framework is openly available, and we could easily demonstrate the interactions between the different modules and control functions in a dynamic environment. We're trying to finish an article on the model and the test cases right now, and hopefully the model can be utilized in future wind farm control projects, taking account the integration of all the control modules, and hopefully with higher fidelity modes also. I'm not sure if I can hear you guys because my...
Can you hear me?
Yeah, okay. Yes. Yeah.
Okay.
So if you have any questions.
Yeah, I also wanted to ask if someone has a question.
Yeah.
Okay.
I don't see that chat. If someone.
No, I think there are no questions. But thank you very much. I think it's really interesting. And can you stop sharing your screen? Then I can. Yeah, thanks. Okay. Can you see my screen now? No. Okay. So yes, so Thanasis started to show you in the first part of the roadmap task. So that was the Simulink model, and we had another deliverable defined there that we call the roadmap paper. And this is a paper further discussing what Irene outlined when she presented the perspective paper, and this will also be submitted soon. For that, we used the same definition of the wind farm flow control and wind power plant control that was defined in the perspective paper presented by Irene just now. And we here wanted to focus on the interactions, like on the practical implementation and combination of those modules. And important for us was that we just want to consider them as conceptual modules, fulfilling a certain control functionality, but that in the future, assuming we have wind farm control that considers both electrical and aerodynamic aspects, that this not necessarily has separate modules for the flow things and the plant control. But for the phenomena, we distributed in four conceptual modules and indicated the timescales on which they are active. And there we have the wind energy management system on top. That is a bit more than operation scheduling, which we did not consider further. And then we considered here that, or like we said, okay, we have this wind farm control, and right now wind farms are operated using wind turbine control and wind power plant control. That ensures grid code compliance. And the wind farm flow control would be a new feature that needs to be, well, that we want to integrate there. And in order to look more in the timescales, Irene showed you the figure with the circles. And she also said that there was a lot of information collected in one. And here we tried to separate it into two different figures. So this first illustration here shows the control modules and the different timescales. And on the second figure, we defined the timescales of the power system operation. So you see here in the middle the frequency reserves that Irene also showed you on the different timescales. And on top, we indicated different parts of the wind farm or wind energy system. And where you can see the, for example, the wakes between two turbines that are occurring at the same timescales to indicate that there might be something we have to be careful about. Yes, and Thanasis showed you the practical implementation of an example for the integration. And in this paper here, we identified challenges of integrating the electrical and aerodynamic aspects of wind farm control. And here I just wanted to mention some of the challenges that we discuss in the paper. One would be the rate of transition and activation, like when do we use wind farm flow control and how do we ensure that it does not interact in a negative sense with the wind power plant control signals. Then we have the actuators and update rates. Since we here, sorry, I think I forgot to mention it, we focus in this article here on the active power and then the frequency support, but we are not considering voltage control and other things from the electrical side. But for the active power, both for the wind power plant control functions, so the electrical aspects and also the flow aspects, would use the set points of the active power as actuators. And so there the control logic has to ensure that there's no conflict. And then we said that, okay, the integration of, you have different control objectives. One is, for example, that you have the grid codes and you have power system services. You might want to provide, on the other side, you want to maximize your power or revenue from the flow side, but also maybe at some point to include structural load reduction. And there can be contradictions and you have to balance them. And then the overall system dynamics and the model fidelity. With that, we mean that right now, when you work with wind and the power plant control, you often just disregard the farm flow, as also Thanasis said, or you just use a really simple representation. And I think you usually just disregard it. But on the other hand, if you model the wind farm flow control, you are not considering electrical aspects. And there, of course, some you don't need to consider, but as we saw in the previous figure, there are some timescales where you might want to be aware of the other parts. Another challenge is the access to the wind turbine control. If you want to perform wind farm control, you want to change some settings of the wind turbine usually. and there can be some practical issues doing that. And then we said, okay, standardization also for the wind turbine control system access would be handy to, if different manufacturers had the same interface, it would be easier to implement wind farm control. Yes, so they were just some of the challenges. And I also forgot that we, as part of this deliverable, had a survey that we sent to researchers that had conducted field tests, and also to industry partners, and asked them for their experience and opinions on wind farm flow control and how to integrate it. And to kind of conclude this paper, right now I would say it's all about communication. So to ensure that these different control features or functionalities work, they have to communicate in a way, and we need to define the interfaces and be aware of how the communication could go wrong. But also, and maybe here we loop back to the workshop in Amsterdam. It's all in this Standardization paper. It's all about the communication that people working with wind farm control and the different aspects of it communicate together to achieve the best outcome. Yes, with that was a presentation of work package 3. And I would like to thank everyone that contributed. And you saw maybe in the papers, we often had a lot of contributors. And I would like to thank everyone. And we had really nice discussions, and I learned a lot, and it was really fun working with you. So thank you. Yes, if there are some questions left, you should maybe just read the papers now, but you have also time now.
Thank you so much, Konstanze. Certainly interesting work, and definitely the need for communication and also the platform for communication. I'm happy FarmConners kind of, functioned in that way also, to provide the platform to bring different disciplines together, at least to a certain extent. We probably need to extend the discussion even further. That's what we've seen after Irene et al. Paper, right? We needed even more stakeholders, players in the discussions. So I think it is a very good start, and I think this discussion is not over yet. It will certainly continue in other workshops and conferences, but I'm really happy of so far the uniformity we have achieved. Okay, so with that, we are actually concluding all the technical work packages of FarmConners. So we will continue with work package 4 right now. I prepared some slides. Let me share. I hope you can see it. So unfortunately, work package 4, which is mobility and networking, we had very high hopes and ideas when we were creating that work package and putting that onto the proposal. We were really excited about that. Having that kind of, first of all, resources financially reserved for that in a project was quite a good opportunity. Me and Ana Maria, we have worked really hard on it. We were looking forward to it, and we had our first in-person mobility also performed, but then Corona happened. So as you know by now, this is probably the work package that is harmed the most due to the pandemic. However, we have adapted somewhat, and I want to show you perhaps some inspirations about this. So we had 3 objectives when we started the project, and when we were writing the mobility, when we had the idea in mind, it was to support the effective execution of the project activities, of course, and then to facilitate the coordination and cooperation, especially because communication being so important for a lot of the aspects of wind farm control that we're doing, and also facilitate the building of network of organizations. So bringing all the stakeholders, or as much of them as possible, together to facilitate better communication, maybe come up with better taxonomies, and also have all these challenges, research gaps, papers and ideas together to have this efficient ground for all these networking activities. However, as I said, we had to adapt over time after Corona started quite early on in the project. We had 3 deliverables defined in work package 4. The first one being the first year activity report, which we have submitted with a lot less activities took place because it already hit in the first few months of the project. And then we had another deliverable that was the lecture on added value of the mobility schemes in coordination actions in Europe. It was planned for the Energy Science Conference, but because of the limited activities that took place, we had to cancel that talk. That is to be replaced, the deliverable itself is to be replaced with a short report by the end of the project in a few days to be submitted. And then we have the final activity report that sort of summarizes all the mobility activities and the new post-COVID activities included in this final report. So the first activity we have had was when Konstanze visited us here in Denmark, in DTU. It was, as I said, early on in the project, right before Corona started hitting Europe, Northern Europe at least. She came from SINTEF to visit us in DTU. We worked at the time for the talk paper, particularly. That was the launch of the common test benchmark for code comparison. We also worked on the showcases at the same time when she was here for 1 week. We shared the same desk. It was really nice to have her also physically there. And then we had to give a long break. After the long break, after summer, we had a miracle, and the borders were open again for a short while. And then Vinit from TU Delft, he came to visit us in DTU, and he was here for about 2 weeks. And then we have worked on the FarmConners benchmark results. You've seen the whole presentation on. He was one of the participants there. So we worked on that together. And then we continuously work on that, also the redefined version of work package 5 after the amendment that has included the further collaboration aspects in it, especially moving towards IEA task 44 on farm flow control. Over there in IEA task 44, we have a work package looking at uncertainty quantification. So with Vinit, we also looked at some best practices there, especially with the toolbox they are using in TU Delft called Floridine. After that, the borders closed again towards the end of the year. And then we have initially planned to visit each other a lot, especially in the beginning of 2022, but it also didn't come to place. Then we decided to come up with something that is called remote co-working. What we did basically was to be in the same Zoom room or Teams room and then worked together for an entire week. Of course, it's not the same as having the physical mobility, being in the same room or the same physical space together. However, it still worked in terms of having the interactions as much as possible and moving forward. It's not as good, but it's better than nothing is a bottom line, I suppose. So in the first one, it was early in January already this year. Konstanze, me, and Michael Smiles from our Catapult, we had the same room. We were meeting pretty much every day, and we went through the electricity market integration work package, so work package 3 a lot. We have contributed and advanced on the market showcases article, and also production of the results and communication with the participants back and forth. So we had the showcases organization and also the paper writing sessions. And we have also looked at the final integration paper Konstanze showed, including the challenges mentioned there. So we have also looked at the survey results and discussed how to put them into the paper. Then about 1 or 2 weeks later, me and Irene this time, we had a remote co-working session, a bit longer than a week. We have looked at work package 3 as well, also looking at those 2 papers, and we advanced on them together. And then we had also including Konstanze occasionally joining into the same room. We were visiting Pamplona occasionally, virtually. And then we have had quite a good progress on the work package 3 deliverables in that sense. And with Irene, we also looked at work package 5 quite a bit, because Irene and me also personally quite active on the IEA task 44 in the work package lead group. So we were exchanging ideas over there, and also ensuring how some of the results in FarmConners can be transferred better to the task 44 activities. Now we have reached to the end of the project. So all of these activities are to be put at the final report, and we will publish it online at the website, farmcontrol.info. Thank you so much. I wish we had a lot more activities to show and a lot more pictures, to show when people were in the same space together, but unfortunately it didn't come to be. So as you know, within the first amendment round towards summer, we have already reduced the activities quite a lot, but we still reserved some money for potential activities. We were a little bit more hopeful about the borders staying quite open, starting from summer to pretty much today, but it also didn't come to be. That means we actually have still a little bit of overspent resources in the budget that we will need to hand back to EU. Yep. Any questions on work package 4? If not, maybe we can continue with work package 5, especially after some of the workshops on the taxonomies and data creation, maybe with you, Anna Maria. Oh, you're muted.
Yes, okay, thank you. Share screen. Okay, can you see it?
We have it, yes, thank you.
Okay, so we were in a way lucky because there was no mobility, and then we could do this task, the development of metadata catalog for mapping the digital asset available in farm control community. Well, it was Nicola Vasilievich and me on this task, and also other people from the other institutions. But unfortunately, or fortunately, depends, Nicola left because he went to Norway. He got a good job proposition and he accepted. And then I left because I'm retired. So, but since I'm very much like this task, I promised Tuhfe to present this, and so I'm here. Okay, the deliverables were this one: 4 fair data tools for wind farm control, which were all the tools that are needed to make fair the data, but we will see it later. And then there was a webinar where most of you, or the people in here, has been participating, and that is done too. Then there is this semantic search portal, which is Alpha Way. We have a portal to search, but it's not really connected. Or not all parts are connected, so that's there is a kind of to do different tasks before doing registering the data. And then the webinar too was not really was not possible. And then there were these resources. Okay, so what is this task? How and why we do this? Well, what was to map the ecosystem of data tools flow that we call digital objects, and all the information available in FarmConners community, because each of you has data, each of you has some information which is useful for the community, but then we don't know each other what each other has. So this is something to make a map, to have a catalog of what is that people has that I can use or it can be useful for the community. How developing this searchable metadata catalog, which is the catalog of all the things that are registered, and why. And there are different whys. The first why is that this is we are in this transition to digital, and then we have a lot of data. And then these data are important for getting information to reach in the innovation part. So without data, there is no there is no digitalization, because digitalization needs data to feed in the data science tools. So without this, the innovation will be much slower. If we can at once pick up data that we need, then it will be much faster. And this is the help of this is information science with data management. If with digitization, we have a bunch of data which is spread everywhere. We don't know where they are. And with information science, we can catalog the data. We can, and then from cataloging the data, there is, if we have a project, we can reach the goal faster. It's important that because it's that I'm going to this one. It's important at two levels, both organization level and in project level, because it's not that this is only for the community, it's also for the organization. If the organization has data which a researcher keeps in his own computer, or there are data which are kind of safe because we are afraid that someone can steal them and so on, this data will never be visible. So then this is a really important link in distributed data. Cataloging distributed data is really important to make visible the organization, the researcher, make internal efficiency, and then also something that the management can reach the data easily to make informed decisions. Inter-organization, of course, it helps a project to develop the goal, to reach the goal. Join force and co-create solutions. And then the last important thing is that, we have a data owner and data users, and then in this way we can connect the data owners and data users with this catalog. The data owner will catalog the data, and data user can retrieve the information about it. So this is really, and then you don't have to move data everywhere. So the data are there, and then can be searched. And eventually, if someone is interested, will ask the permission to you. Okay, let's see. Okay, we need the metadata and taxonomies for doing this, and we had this from previous project, IP Wind. And then the point here is to design a semantic portal. And that is what we have done in FarmConners. So this is to make the data findable, accessible, reusable, interoperable. We need to a series of steps. I think I would like to show you if it works. Video. 2 minutes of this video will make the I don't have it. I cannot do it. Now, where I am now. I've lost my, oh, yes.
Okay.
Yeah, okay. But this CENER is a kind of the platform where we have created the metadata list that can be filled by the user. that want to register the data. And this metadata will transform the data into a special format that can be used in the platform to retrieve the data. And the platform that is being created in FarmConners is Sesame, which is I mean, it should be the front end with CENER, with the metadata catalog, but it's not finished. So it's only these are the metadata and the taxonomies that I used for this, which are registered on CENER. And this is how it looks the Sesame and the ShareWind. Okay, this is the structures. When we make a catalog with the Sesame, the catalog will have some data sets below, and the data set will have the distribution list, I mean, the information about the format, and eventually the link to the data. So this is an example of what we can catalog, but we can also catalog, make it a ShareWind catalog with different subcatalogs. For instance, there is before it was an Eguinoa catalog. Now we have the Eguinoa catalog and the FarmConners catalog. And under this catalog, there are other data sets that we might search for. And then there is the final, the European Energy Research Alliance data. It's a project as a thought about to make the catalog under ShareWind, where the ERA data catalog will have the ShareWind catalog and the ShareSun catalog. This one is the catalog for the sun, for the renewable energy sun, and then we'll have other renewable energy catalogs. It's a way that the ERA can offer service to the associated to try to find the data which are available under ERA. This is how ShareWind looks. If you can filter for data sets, you can filter for when you find the catalog, the data set. You can filter by, okay, and then there is also a dashboard. I wish I had more time to show in an example, but I think it doesn't work anyway. That if there are some questions.
Well, in the chat, I already put the link for ShareWind, where you can see the little drafts we created back in October workshop. But one of the questions I had in mind was, since we have some people also involved in task 44, how to take it further, because it's important. Platforms like this, it's going to have a longer lifetime than the projects themselves, right? And I know you've been in contact also with the other task on digitalization, task 43.
Yes.
So, yeah.
Also with task 41, which they are going to use this catalog ShareWind to register data. Unfortunately, it's not. There should be a project that brings to the level that there is an integrated system, so you can access, fill the metadata, and then go to the ShareWind and then search. The registering and the searching should be integrated. But so this is what is missing, but it's fully operational if someone wants to do it. And the beauty of this is it's modular, as you've seen here. You have each project has its own catalog. So this catalog can be extracted with JSON in some forms, an RDF, and then can be moved to another. It's interoperable. That's why we have done it, because it's fair. So there is no need that, there is no fear that this, whatever you put there, it will be stuck there. Because it's quite interoperable.
Yeah, you can extract them rather easily. Irene?
Yeah, okay. No, according to your comment, Tuhfe, probably we could think, or is it feasible to think on how to integrate, for example, the wiki in task 44 with this metadata? Would be this feasible, or?
I'm thinking it's one of the ways, right? Another way we can do is that although it is sort of easy to extract and things, but first people need to know about it, right? So I'm thinking, Anna Maria, since you're emeritus with us for another year, before you leave completely, maybe we should invite you also in one of the talks for work package 1 in task 44, where this is.
I would be very happy to contribute there, because I mean I've been working on this for the last 5 years.
Yeah.
So I think now it is something which is usable, and would be pity to lose this what we have done, because it is I think it's the smartest thing that we can do with the data. I mean, to register somewhere, because the catalog can be seen by everybody, and no fears that people misuse data and so on. There is something which is like I've like this. It puts people in contact.
Exactly.
Irene, you're not convinced?
Yeah. I'm convinced of the usefulness of these tools. It was more an open question on if this is feasible. For example, Tuhfe might be aware of the details on how the wiki is also being built for the task 44. So probably is one of the points to raise with the other work package leaders.
Yeah.
About the metadata and taxonomies related to the metadata, this is I mean, there is something which is called metadata challenge it's a Swiss platform, and we are looking at what is around in terms of metadata and taxonomies and vocabularies, and this is the most complete that you can find at high level. Of course, when you want to have richer metadata, then you have to go and you have to produce them for going to the details in a field.
Okay, thanks.
Okay, thanks a lot, Anna Maria. We'll definitely keep you and everyone else updated regarding on how this metadata catalog grows further within the task 44 activities, and also maybe with other projects. Also, feel free to let us know if you're planning to use that also internally. I'm thinking, for example, the mid part that you were highlighting earlier, it can also be used for kind of an advertisement, right, for the data providers. So they can show what they have, and maybe researchers can reach to them and use their data. We were having that idea for example, some of the benchmark test cases that we've used. So it will be a nice advertisement for a lot of people, a lot of data providers, if people were to look for certain data sets, because they don't have to share the data set there. They're just sharing the information about the data set, letting everybody know that it's available. And then people can reach to them and ask for, ask for access, basically. Okay, then thanks a lot. We have the last work package left for our discussions, and that's going to be the work package 6, which is the management. And of course, the management work that is left by the end of the project is more about reporting, both technical and financial reporting. So Gregor, I'll leave the word to you.
Essentially, what I started out with at the beginning is that we had these amendments. They are through the second amendment. We didn't even talk about much because it essentially was completely budget neutral. So for most of you, it didn't really have any implications. For some of us, it meant in part quite frantic work from getting the new organization to actually be in the European system and so on. But that might be a side story and would be one of those stories that are better shared over a beer after the meeting, which we unfortunately cannot do still. But as mentioned, this project comes to a close at the end of the month, which is on Monday. So after that, we will have to put in a final report and to also do the financial reporting. Our controller, Hyllested, should be here in a couple of minutes to get you a bit more details on the financial reporting. For the final report, there is a template that I tried to find just before, but couldn't. But what I can show you instead is how it currently looks on the Sigma, the system for grant management. We also often call that ECAS because that was the name that the system had beforehand. And what we see here is the list of deliverables, where we see there are a few things pending, which we should be talking to the respective owners for. There's the common test benchmark results, but that's a bit overdue only. Also, the recommendations for certification, I think we got some extension of that from
the project officer,
from Loic, who's our officer. And so we got 2 more that are red and a couple more that are not yet read because they're at the very end of the project. But Tuhfe and I, together with Khan, will have a few more hours until Monday afternoon to fix some of those. One thing that we really didn't put in enough yet are those publications, but I think Tuhfe is well aware of any of the publications that we actually had within the project. So we'll also put those in. If there's any publication that had a FarmConners acknowledgement, which you didn't tell us about yet, please put it in the chat. And other than that, it's essentially just some of the typical reporting stuff that we are going to do for you. And if we need anything, then you'll get a mail from us.
I do have a question regarding the publications bit. So, for example, for some of the papers, for example, market showcases, we are planning to submit it by Monday, which is the end of the project, and we can definitely freeze that version and put it up. However, we will not get, for example, the DOI. Even if we're submitting to Wind Energy Science, there is some time it takes for the editor to be assigned, etc. So do you suggest then, or is everybody agreeing to the suggestion of also freezing the version in Zenado and put it with DOI in this format to the system? Like Nicola's deliverables, for example. Or maybe we don't necessarily have to have the OI for this page.
I think without the DOI is also going to work.
Okay.
It's not a new thing for the EU that some of the publications might come after the official end of the project.
I can imagine, yeah.
They've been in that situation probably since Framework 1. And so they are used to having things a bit later.
Yeah, and also one question, if you already publish it in Zenodo, depending on the rules of the journals, probably they can say that it's published somewhere else before. So
okay.
This may give problems, right? I'm not sure. Probably others in committees in journals can say. But
yeah, normally if you're submitting, that's exactly right. And you get these plagiarism softwares typically at the editors that will tell you if some things have been published before, and even if it's only parts of it. So better not putting it up on Zenodo and just going directly for a proper publication.
Okay.
And even if it's a bit delayed, I don't think that matters much. It would be nice, as I mentioned, also there's a review meeting at the 26th of April. It would be nice if at that time we actually had at least submitted. But as you say, you're planning to submit on Monday, so that should be possible.
Yeah, for pretty much all the deliverables, we had the internal deadline of next week tops. Yeah. Yeah,
exactly.
Also to keep the momentum, because you've seen a lot of the works is very, highly authored, and it's important for everyone to stay focused and finish with that. Most of them are in the final shape anyway, so yeah. Okay. Then I will do that packaging and updating of all the deliverables, including explanation about the mobility deliverables that we couldn't deliver. So that's going to be discussed probably further in details in the review meeting with the project officer, I imagine.
But we also explained a few times to him that the mobility grants were a very good idea in the very beginning, and then reality hit us.
Unfortunately, yeah.
Yeah. So maybe then, because that was essentially all I had, maybe then we'll wait a few minutes to do a coffee restock.
Yeah.
No, there she is.
Yeah. Hi, Karen.
Hi, Karen. We just came to the point where we either would have had to put in a short coffee break waiting for you, or where we just have you on. And I think now we will just have you on to tell us a bit about the financial reporting.
Yes, the financial reporting is as it has been through the project, and you will be contacted by our financial officer on what and when to deliver. So that is the same, but they cannot contact you until the report has been opened in the system. And it will be when the period is closing. For the technical report, you have to make a periodic report, as you have been doing for all the other periods, but you also have to make a final report. And I just made a quick slide here on that, and I have simply taken it from the grant agreement. I'm wondering if you can see this.
Yep.
Yep. Maybe I can also put it up like this. And as it says, in addition to the periodic report, for the last reporting period, the coordinator must submit the final report within 60 days. Final report must include the following: final technical report with summary of publications containing an overview of the results, their exploitation and dissemination, the conclusions of the action, and the socio-economic impact on the action, the final financial report containing a final summary of financial statements. and that is created automatically by the electronics exchange system. So, and then this is just a certificate on financial statements whenever that is needed for some of the partners. So these are the requirements for the final report. Again, it's been generated on the portal, so we'll have to wait for the template for it. But at least here you can see what it is expected to include. Any surprises?
Irene has a hand up.
Yeah, one quick question. Since the final review is on the end of April, 26th, I guess the project officer will want to have it in advance, the reporting, in order to go through and make the questions. So did you receive any deadline from the project officer on which is the internal, let's say, internal deadline for submitting the reporting, in order to prevent our financial departments and so on, since they are always quite busy and yeah, you know.
That is a good point. We have not received one from him beforehand, but I think it's a good question to raise to him. Probably we cannot get an answer this week, maybe even the next week, because they are evaluating the EU proposals, as you might know. So, but we might get an answer at least by mid-March as to when to do that. But internally, to be on the safe side, probably within the month April should be fine. The grant amendment said 60 days, but maybe.
Yes, you have 60 days to do the reporting, both the technical and the financial. Yep. And we need the system to open for that. And the financial reporting you can certainly not do before this review, because that is done after the review, after your final travels and costs and so on. So
okay. So Karen, the final financial reporting will be after April then?
Yes,
okay.
It will. But I think it's a good idea to have a conversation with the project officer how to deal with it for the final review. What are you going to do? But I take it that you're going to do your presentations as you do with these reviews and inform on the results. And so in that respect, it is the material you then have for the final report.
Okay. That sounds easy.
Yeah. It's a bit more time than we thought. All right.
Yeah.
Good.
Good.
So, yes.
Thank you so much, Karen.
You're welcome. So, and if any questions, you just call me.
Thank you.
Okay. Have a nice afternoon.
You too. Thanks a lot.
You too. Bye.
Bye.
Okay. That brings us to the very last item on the agenda, which is any other business. So anyone has any questions they want to raise? Any comments?
I would only have one comment. First, to thank Gregor and Tuhfe for leading the project and make us such interesting, and yeah, and we had quite a lot of fun, even if it was from home. But yeah, and also the VP leaders for the work they've been doing all along the project. So that's been great as a collaboration effort. Thank you.
Thank you so much, Irene. Pleasure is all ours. Thank you. All right. Thanks a lot. Yeah, well, basically, I think the biggest sort of continuation of FarmConners will be in the platforms through IEA Task 44 for the people who are involved. I think the majority is involved. And of course, we will see each other in hopefully conferences, maybe in person at one point, maybe in Torque already. We'll see most of you, hopefully. Fingers crossed. Otherwise, in other workshops and other platforms, next projects, we will continuously keep an eye on the coordination action calls anyway. So you might get another email. Yeah, exactly.
Also because, well, first of all, it's fun. And second, it's one of the easier calls to get. So this market uptake support, I think it's still in the new framework program. And that I think had significantly higher chances than one of the usual programs where you're supposed to do real hard science and not just talk to your nice colleagues. And with a bit of luck, by the time the next one rolls around, we're actually allowed to come together again, which would be really nice. Talking about which, one thing we missed out on for this project is, and many of you have already started with that, is the group picture of the end. So if the rest of you also could switch on your cameras. Since this is recorded, we don't even have to wait for some particular moment to look very funny, very strange into the camera, but we'll just take the best image available.
I would like to make a comment out of the box. Politically, we have today invasion in Ukraine, and the importance of renewable energy and a unified European energy grid will become important more than ever. So we are working on the right side, I think, here with those projects.
Exactly. Better European wind than Russian gas at the moment.
Exactly.
Also in the future, not only at the moment.
No.
Yes. Good. On that, yeah, forward-looking note, let's call it. Thanks all for being here. Thanks for your participation. It was fun. Thanks especially a lot to Tuhfe, who's been essentially managing all the project nearly alone.
Super fun. Thank you so much. I'm going to be depressed a little bit after this project ends. I've been saying for the last week. I'll feel a bit like nothing left to do, but
there's plenty to do in Train to Wind.
yes, here we go. Looking forward to the next one. But thanks a lot, and we'll talk later for finishing off the articles and probably the revision of those articles and things. So we still have work to do, that's for sure.
Exactly, and I mean there's that here apparent of the IEA task, which just continues to be a nice discussion club.
Exactly.
Unfortunately, with a bit less funding.
Yeah, but a bit bigger consortium. So we also have the cross-Atlantic people, and yeah, it's nice. Which we have meeting already for the outreach work package next week. So maybe I'll see you there already then, or earlier for all the other articles. Thanks a lot.
Good. Thanks a lot, and
bye.
See you at one of the next conferences.
Bye.
Thank you, everyone.
Bye.
Thank you.
Bye. Bye.
Bye.